Well, welcome everyone. I'm Hope Medina with Shums Coda Associates, and I happen to be one of those fun-loving people that thought sustainability and energy sounded like a good realm, and I fell in the hole, and I never got out. And I'm okay with that. I've made it very comfortable there for me. But just so you understand where I'm coming from, I'm certified to perform in all trades: electrical, mechanical, plumbing, accessibility, building. So I come from a perspective of understanding the project as a whole as to how to implement the energy and sustainability items that are out there. So with that, this is an interactive class. You have questions, feel free to ask your questions. I would guess, chances are, if you have the question, there's probably others who have the question. Jeff's going to keep me on point to make sure that I give more breaks in all of this. So, all right, today we're going to talk about the thermal envelope. And we're going to look at both the commercial side and the residential side of the 21 IECC, including the amendments that were made in several jurisdictions. So, really quickly, how many of you work in Aspen? Okay. How many of you work in Pitkin County? Okay. How many of you work in Eagle City County? Okay. How about Glenwood Springs? Carbondale? Okay. So we have a good mix. What I will let you know is I do have their amendments included into it, so we'll look at the base code of things and then the little tweaks that happen with the various jurisdictions, how they amended their thermal envelope. So with that, I'm going to ask y'all, when is a building considered to be commercial under the energy code? I heard murmurings. Who wants to be brave? What was that?
More than 3 stories?
It is considered to be commercial if you're an R2, R3, or R4, more than 3 stories above grade. So, out of the energy code, it actually has definitions of what a residential building is, and that's a single family, 2-family townhouses. It also includes R2s, R3s, and R4s that are 3 stories or less above grade plane. So that means you could be doing a multifamily project, building it out of the IBC, and then going to the back of the IECC to utilize residential provisions in that quote-unquote building that you built out of the IBC. So the energy code says anything that doesn't fall under as a residential is a commercial building. Now, how many of you do commercial multifamily? Okay. Are they straight multifamily, or do you have mixed use going on? Mixed use, all right. So here's where it gets to be a lot of fun. So, if it happens to be considered a mixed use, it's a 3-story building, and let's just pretend that that bottom floor is the commercial portion, right? It's a coffee shop. It's a beautiful coffee shop, wonderful coffee shop that serves all the residents in those upper 2 stories. Those 2 stories above that commercial is considered residential out of the energy code. So now what you're going to do is you're going to take the provisions of the commercial side, apply it to that 1st story, then go into the back of the book, take the provisions of the residential and apply those to the next 2 stories of the structure. So because, as I mentioned, this is an interactive class, what is a possibility of how you would demonstrate that on a set of plans? Because is the thermal envelope requirements the same for commercial side as the residential side? No. So how are you going to be able to demonstrate this on a set of plans to ensure that you present your design appropriately to the building department, that the building department can say, yes, these plans meet the requirements that you find in the code? Then they're able to go out in the field, and so that the contractor is able to understand and know exactly how this building was designed. Any thoughts? Anybody want Hope to go to the next slide and say, just show us, because I'm curious? All right. Well, how about this? One option you can do is you can provide 2 reports. One that's a comm check to demonstrate the thermal envelope values meet the requirement of the code for that first floor. And then for the top 2 floors, you'll end up providing a res check. And between the 2 documents, you would be able to demonstrate that the thermal envelope of this building meets the appropriate side of the code book. Now, there is a caveat to this. If the design that you have is the commercial on the bottom and residential on the top 2 floors, then when you are producing a comm check for that first floor, it's going to provide information as far as slab edge, floor, if it happens to be a slab floor, whatever the case may be, walls, windows, doors, but the information it will not contain is the roof. And that's because the roof is part of the residential portion of the thermal envelope. So in turn, when you are producing a res check for the upper 2 stories, what you're going to do is you're going to show your walls, windows, doors, and this one will include the roof information. What it won't include is anything that has to do with below grade walls, slab on grade. That information pertains to the commercial portion. And like I said, the 2 of them together typically will then create a complete thermal envelope and demonstrate compliance. Now, with that being said, how many projects do you see where 1 story has an R value of, we'll just say an R20, and then the next 2 stories has an R value of an R30? Or typically, what you see is it's either all an R20 or it's all of it is an R30. And what you're able to do is really incorporate some flexibility and tradability. Now, you can't trade components out of that first floor to go into the top 2 floors or vice versa, but for that first floor, you're able to really kind of navigate a little bit. You might have the ability that you're going to put in, R20 plus an R5 continuous insulation, because if you go and look in the Group R column in the table, it usually includes a cavity and continuous now when we're talking about Group R for walls. So there are some designs that are comparable for both of them, so you don't have to do 2 separate types of walls. And the nice thing is, too, if you think about it, for the top 2 floors, you probably have a little bit more flexibility in all of it because you get to count that roof into your calculations, whereas you don't necessarily get to count, well, you don't get to count the roof for the commercial side if it's that bottom floor. Any questions about mixed use? Now, I obviously gave you an example of where they're stacked on top of each other. I've also had projects where they're next to each other. So that's also a configuration that's fun, that becomes a mixed use, that the project's going to use both sides of that book. All right, let's talk about the commercial side. Quick question. Does the image on the screen scream, I'm a commercial building? How many stories do we have? We have 4. Now the question is, what if this bottom floor was garage? Still, you're absolutely right. I don't know if I put that in here, but please be aware that podium construction, Derek, you're going to have to do penance for missing the great intro.
Sorry, everybody, you got my steps in.
So podium construction is something that pertains to the IBC, and that's really creating that 2-building concept so that you have, you know, your area and height limitations and your type of construction that kicks in. When it comes to the energy code, we do not count podium building at all. It is a single structure that will end up having 4 stories. So then you're kicked over to the commercial side. So please be aware, podium construction does not count in the energy world. All right, so one of my absolute favorite sections in the code happens to be 103.2, whether it's residential or commercial. But we do have some amendments that have come into this section. So Garfield County requires that all commercial buildings have to commit or submit a ComCheck report or an equivalent software showing compliance for your envelope, mechanical systems, and lighting. So if you're working in Garfield County, realize you're going to be utilizing ComCheck, which in all reality is a wonderful tool for everyone because it really does help in guiding in your designs and ensuring that you're meeting the requirements out of the energy code. Another community, anybody here work in Newcastle? Okay. Newcastle does require that at least 1 paper set and in digital format is provided, and the construction documents have to be prepared for code compliance by an approved third-party energy consultant prior to submission to the code official. So if you end up working in Newcastle, just be aware that there is this requirement for it. All right. So before we can actually have the discussion about the thermal envelope, one of the things we have to be fully aware of, because it really determines how you're going to treat the thermal envelope, is which compliance path is utilized. So a lot of times I'll see on plans that they say, I'm going to go prescriptive. Well, when you say prescriptive, I need to know which category or option within the prescriptive umbrella you're utilizing. Is it the R value option, right? The one that we probably utilize the most, everybody thinks of, oh, it's an R20 in the wall. Or are you doing the U factor, C factor, F factor option? Or are you utilizing that component performance alternative, which happens to be ComCheck? Anybody know when the component performance alternative became a legitimate option within the energy code? Anybody know what edition it became recognized in? You can shout it out. Take a guess. 2012, little too early. Anybody else brave? 18 is a little late, so that leaves you with 15. There we go. Yeah, so it became a legitimate compliance path option in the 2015 edition of the IECC. Prior to that, if you submitted a ComCheck It was considered as an alternative method, means, and material approach. Now, the nice thing is code officials did not make it difficult because it helps them, right? They made it an acceptable practice that you didn't have to go through the process that's established to utilize an alternative method, means, and material. It was just readily accepted. So the next option in there is the total building performance. This is where you have modeling going on. You're trading more than the thermal envelope. You get the ability to trade anything that's in that list potentially as to how you want your building to perform. 407. On the commercial side. On the commercial side, it's 407. On the residential side, it is 405. Yep. The last option is really kicks you out of the IECC altogether and you don't pay attention to anything that's in there. And that's ASHRAE 90.1, which is an energy standard, not an energy code. Everybody understand the difference between code and standard? So how the code is developed is it's a consensus process. It's an open consensus process. Anybody can participate in it. But ultimately, it's the governing members, code officials, who have the final say about what gets into a code because they get to vote. In a standardized process, they do, and it is ANSI certified, so they have to go through and demonstrate their process is an ANSI certified process. But basically, you submit something, it gets heard, they decide it, then they can say, we say no, they can resubmit it, it can have a negative ballot, and it can keep on going until it gets quote unquote resolved. So it's just a slightly different process in all of it. And in the past, ASHRAE 90.1, whether a project chose to go with 90.1, was not determined by the architect. Anybody know who determined whether or not the project was going ASHRAE 90.1? Mechanical engineer, absolutely. And that's because the energy code back in the 12 really kind of kicked it off. But in the 12, or in the earlier editions of the IECC, the mechanical provisions were not as robust. And it was geared towards those simplified systems, right? It's one zone, one piece of equipment that was handling it. So your Starbucks would fall under a simplified. This would not fall under simplified. So this project probably would have went into ASHRAE 90.1 because they had more tools that really governed how you're going to address the mechanical systems. But now the energy code is almost a carbon copy of what you get in 90.1. So more projects are probably, you see, using the IECC, whereas in the past it was 90.1. But keep in mind, if they do go 90.1, it's all or nothing. You can't cherry pick saying, I'm going to do mechanical out of ASHRAE, but the thermal envelope out of the energy code. One or the other. All right, so let's talk about a couple of amendments here. So for Aspen, and sorry guys, I have to look at it exactly. I don't have everybody's amendments memorized. So for Aspen, it says that commercial buildings have to comply with 401.2.1 or 401.2.2. One is you're going to go with the prescriptive path of compliance for commercial buildings. So you're going to do 402 through 406 and 408. And then 402.2.2 says you can go with ASHRAE 90.1, but the compliance path out of ASHRAE 90.1 that you will have to follow is the performance path, which is Appendix G. And this is only an amendment in Aspen, but I know we had some people who were working in Aspen here. So, all right. We've talked about what a thermal envelope, that's what we're going to discuss today. What exactly is a thermal envelope? What's the purpose of the thermal envelope? I'm asking you all, so I can drink a sip of my coffee.
Separate the outside from the inside.
Very good. That's a simplified version, but absolutely what you're doing is you're separating that conditioned space from the unconditioned space, which typically is the outside, but you could have a storage unit that isn't going to be heated. But you're absolutely right. It's a boundary separating that all. So when you look at an image like this on the screen, which I realize is probably hard to see a little bit, what are some of the things that come to mind that you want to think about when it comes to the thermal envelope?
Continuous.
Continuous, absolutely. That is an excellent, excellent statement. Because I'll tell you, so I used to write up all the time because the depiction of the thermal envelope was very rarely ever done on the plans. Until the 2012 edition of the IECC, it wasn't spelled out as a requirement in the Energy Code, but there were a lot of jurisdictions that required that to be submitted. So I would have to say, hey, it appears your thermal envelope is not continuous. I used to say, I should be able to trace it without lifting a finger. And unfortunately, as some of you have heard, I had a response back from an architect who said, if you're too lazy to do your job, then maybe you should find a new job. Because I used the term lift a finger. And I never put it together because I thought I was explaining it well, like, you know, should be able, because this was back in the day of paper plans, okay? So this was a long time ago. You know, I thought that that made sense, that I was expressing it in a good manner. I never thought about that it's also, you know, a term used for being lazy. So now I say without lifting a finger because there's a break in the thermal envelope. So the good thing about this story is, you know, like always trying to find a positive in it is it provides an alternative view that I now know, okay, I need to word things a little bit differently, not so that I'm not, you know, I guess offending others. But, you know, it works out well. So continuous is absolutely correct. What else? All right, let's walk through this. So I'm going to look to see first. So when I look for a thermal envelope, there's some things I look for. I look to see, okay, so where is the insulation for the roof being placed? Is it above roof deck? Is it in the attic? Just so I have a good idea of where I need to be looking for that thermal envelope and potential areas of disconnection. Above grade walls. Are they showing me that maybe they're metal? Are they wood? Just because sometimes that also provides little hints for the thermal envelope. Do we have any below grade walls? And when I look at below grade walls, specifically, especially in something like this, I'm going to look for garages. Because garages are notorious for having issues with the thermal envelope being continuous. Floors. Am I having to worry about any floors? Looking at this image here, does it look like I have to worry about any floors as part of the thermal envelope? Yeah, there's definitely some distinct possibilities here. And slab on grade. Bless you. Is the slab on grade that's being shown here, one, is it part of the thermal envelope? And if it is it heated or unheated? Because that also changes the location of what we're looking for that thermal envelope. Meaning, if it's unheated, then the thermal envelope is going to reside down those foundation walls. If it's heated, now I also know that I need to pay attention and ensure that we have insulation underneath that slab. And that changes where I look for demonstrations of where the thermal envelope is. Now, if we look at the image on this screen, is this a continuous thermal envelope? I hear no. Why would you say this is not a continuous thermal envelope?
Stops at slab. Agreed.
All right, you guys are all catching a few things. So right here, one, there's two things we have to pay attention to. A lot of you caught this right here. Now, the question is, and you guys caught it for, I heard two different reasons why you caught it, and both of you are correct on that. One, if this is a heated garage, then that insulation should be extending all the way down. If this is an unheated garage, then we should have insulation that continues within this plenum here, because that's the new designation of where the thermal envelope is. But either way, it is no longer continuous because we have a break happening in this particular location. Now, what I will tell you is the garage was heated, and so it would have had to extend all the way down, plus, which a lot of you do this up here with your garages, your grade garages and everything, is there was going to need to be a door, because you can't just condition the space and not have it enclosed within the thermal envelope. You can't have a big, giant opening for it. Now, the one thing that didn't get picked up on is the floor insulation. Why is that floor insulation there? Is it part of the thermal envelope? Nope. It's there because we have to have horizontal separation for our occupancies, so that insulation is part of that rated assembly for that horizontal assembly. So, kind of brings us to this concept. What all, let's see how I want to put this. What components of a building does insulation serve as various functions? What are those functions that insulation within so many assemblies actually serve, including but not only as thermal resistance as part of the thermal envelope? What was that? Yes, sound. What else? Fire. Yep, we just talked about fire-rated construction. And including with that fire-rated construction, here's where it gets to be really fun. You guys didn't know how much fun we were going to have today, did you? So when we talk about fire-rated construction, if we decide, hey, I'm going to put some spray foam in a cavity, what do I have to do with that spray foam? What is that spray foam considered? Foam plastic. What do we have to do with foam plastic? We get to go to chapter 23 of the IBC that deals with foam plastic, and it requires that we have to have an ignition or thermal barrier. So that entails a list of materials that can be that ignition or thermal barrier. One of them happens to be mineral wool, or bat insulation can be utilized as that. So sometimes when you see that bat insulation over that spray foam, it may not be part of the thermal envelope of it. It may be there because it's just being that ignition or thermal barrier. What else? How about vapor retarder strategy? It can play a big part in the vapor retarder strategy of a design. How about air barriers? We've got insulation that can be considered as an air barrier, which is part of one of our components of a thermal envelope. We really shouldn't have insulation without also having an air barrier. So, did I miss anything on here? Nope. Between all of us, we got them all. All right, so here are some of the more often utilized types of insulation. And what you see on the screen here came from the insulation manufacturer. So this wasn't Hope just did a search on Google and got this information. I talked to my colleagues in the manufacturing world, and they gave me the average values that their industry produces for the types of insulation. So as you can see, we go all the way down from a 2.2 all the way up to a 7.2. So that's a significant difference about what we get as far as R value. Now, one that's not on there that's on a different slide is mineral wool. Mineral wool gets us about between an R 3.8 to a 4.3 per inch, which mineral wool gets called out all the time for fire-rated assemblies. So it's fairly comparable, in fact, even better than fiberglass bat insulation as far as R values go. Not better production or anything. All right, when we talk about thermal envelopes, one of the things that is in the code now on the commercial side that helps with documentation of our thermal envelope is our insulation certificates, right? Now, our insulation certificates are there, and they're required to be placed there when we have a type of insulation that doesn't have that R value plastered on it, right? So mineral wool will have it plastered. Bat insulation has that R value plastered on what R value this material is, but when you use spray foam, right, does it magically have an R value that shows up when it dries? No. So we have to know what type of insulation and how much of an R value it is. So how we do that is have an insulation certificate provided by the insulation installer. Now there are some requirements with it, depending on the type of insulation that it is. If it's blown-in insulation, we need to know what the thickness is, what the settled thickness is, what the settled R value is going to be, the density that it was installed. We also have to know how many bags were utilized and the coverage of area those bags entailed. Spray foam, we have to know what's the R value. Because can you go up to spray foam, look at it, and know that it's one of the 4 types of spray foam? No. They usually look fairly similar to each other. And when I talk about the 4 types of spray foam, we've got low density, which is our open cell. We've got mid density, which is our closed cell. We have our high density, which is typically used for above roof deck. And then we have our sealant. So that's something that would be utilized more along the lines for like air leakage. Installation around windows type of deal. But that one is it's not a fast expanding foam, so it can be utilized for those windows. And then insulated siding, you just have to tell us what that R value is if we don't have it. And then that certificate or notice has to be installed. It also has to be placed in a location that's conspicuous and makes sense. Now, question for you all. When should you be seeing that certificate?
At the installation inspection and at the final.
Absolutely, you hit it right on the head, because I'll be honest with you, I've gone out to projects that they hand me, because I'm not there all the time. Sometimes I go and make guest appearances. I'm there for a couple of weeks. And they hand me the stuff, and I'm like, oh, well, that's interesting, because you just told me that you put an R20 in this wall. Your plans say it's supposed to be an R30. What happened here? Oh, well, so if you get it at the tail end of things, that creates a whole lot of issues. Technically, as soon as I go in to do an inspection, I look for the ticket that's typically stapled to the stud or taped to the stud, and it lets me know that, okay, great. It is, because it's spray foam, lets me know it's 5 inches, it's got an R6 value, so we got an R30 in that wall. Perfect. I can move on with my day. So this is so incredibly important and probably the least, I'd say enforced maybe, concept. But those insulation installers, they have them ready to go, so just start getting into the habit of asking for it as soon as you're going out there for either the inspection or as a super, you're going out there walking your job, making sure that all of that's there for you. Because the reality is the architects designed these projects to perform a certain way. To get them to perform the way that they designed it, you have to install what they designed for. All right. This is just commercial. We'll hit residential in a little bit after we go through all the fun of commercial. All right, so this is our R value table. We're going to focus on the R value table and not necessarily the U factor, C factor, F factor table, just because I think it's a little bit easier to understand it through the R value table. As you'll notice, here are the communities that we're looking at or we're talking about. The middle column lets you know what edition of the code they have currently adopted, at least as of when I put the class together. Hopefully nothing's changed since the last month or so, but it could. And then whether or not they amended the table. So right now, the only community that has amended that R value table is Aspen. So we are going to take a look. Hopefully it's showing up. I apologize. I know that it is really small, but I was trying to give you some good insight. But these are the requirements that you would find within the table if you are anybody but Aspen in climate zones 6 and 7. Anybody designing for 5 right now? I do have a couple of slides dealing with 5, but. And then these are the requirements if you are designing for Aspen. So if you notice the values that are listed in blue are the amended values to what you would see within this table. Make sense? I hope. Okay. So we're going to walk through the components that we have within this table to get a more in-depth view of what we're looking at for the thermal envelope. So the first one I want to talk about is the insulation entirely above roof deck, which we see a lot of in here. If the insulation is entirely above roof deck, you have to demonstrate that you have a minimum of an R30 continuous or 35, or if you're Aspen, an R40. Whatever the number is up there, you have to ensure that you meet that as a minimum. Now, with that being said, what do we typically have happen on a roof with the insulation entirely above roof deck?
Taper.
Yeah! Are you looking at my slides? No. So we got tapering going on, and we want tapering going on because we don't want our snow, we don't want our water hanging out on our roof. We want to drain it away and off the roof. So my question for you is, you have to demonstrate, we'll just say an R30 continuous insulation. How do you demonstrate an R30 continuous insulation when you are tapering that insulation? You both are right. So basically what they're saying is you can do an area weighted average of that roof, and as long as that area weighted average meets what the average or the required R value is, the R30, since we're just using that one, does that seem like a lot of math? How many people here love doing math? I always have one person who loves doing math.
I don't like doing the math. I'd rather just do a minimum insulation and call it a day.
Well, that's really good because I'm going to give you a way of doing that. So one of the things that we have determined, because the reality is, if you're trying to get an area weighted average of an R30, what is that going to entail? To get an average, that means you have to have something higher to offset what the lower is going to be. So as a rule of thumb, if you're required to have an R30, if you say, I'm going to install as my baseline an R35 with tapering to average an R30, I'm going to accept that all day long. Am I going to ask you to say, okay, I'm going to have 300 square feet that's going to be an R10, and then I'm going to have 400 square feet that's going to be an R30, and 700 square feet that's going to be an R35? No, not unless there's a reason I would have to. I would accept the concept of I'm starting off higher, knowing that there's going to be times that it's going to be a lower amount, but the overall area weighted average is going to be a 30 once I start off with a 35. Any questions about that? And I guess I should ask the code officials that are in the room, is that and maybe it's putting you on the spot, but is that something that you would readily accept?
Well, that's how we get there.
Yeah. All right. So there you go, from Derek, who was late. All right, so here's some areas you can see here where there is a significant dip in that amount of insulation that you're going to see out there. All right, the other thing is typically, or it is required that when you're doing that insulation entirely above roof deck, or you have continuous insulation, you're going to have multiple layers of continuous insulation. You have to stagger the joints and seams of that insulation. And guess what? When that insulation is going to be installed above roof deck, you have to install it in a minimum of 2 layers. So you will be staggering your insulation above roof deck. Now, here's a good one for you that nobody can see. I'm just going to tell you what it says that's important. Everything else, don't worry about it. It says 3 layers of thermal insulation. Each are 2 inches staggered overlaps. How many of you would say this is an okay, good description on a set of plans that I can deem check mark, we're good, it demonstrates compliance?
I would say 2 foot staggered.
Well, all it says is staggered overlaps. It says each thermal insulation, 3 layers, thermal insulation, each of them are going to be 2 inches. There we go. Or even overall. We don't know what the R value is per inch. We also don't know what type of insulation it's going to be. It just says thermal insulation. I just showed you a screen that had 8 different kinds of insulation on there. And I have other slides that shows more insulation on there. So there's not enough information for us to go off of to even try to guess whether 2 inches would work. Because if we did 2 inches of batt insulation at, let's even say a good one, a 3.8, that gives me, at 2 inches, Hope's going to stall for a minute, 7.6. 7.6 for each layer. If I multiply that by 3, it gets us like, what was that? Somebody could help me. 22.8. There we go. Thank you very much. So that is definitely not an R30, right? So that becomes an issue. So there's also a requirement just for everybody to be aware of. In 103.2, there's a list of items that are required to be placed on the construction documents. And when they talk about the construction documents, they need those rolled up sheets of paper. It says you have to specify the R value of the insulation. You also have to specify the insulating material that's going to be utilized. 103.2. Yep. And the reason why we want to know that is because, just like as I mentioned before, insulation is used for many things, right? Especially when we start talking about like vapor retarder or air barriers. Those things are important to know. So this one has a few issues with it. It should list what the insulation is, the R value. Then we have this one over here that just says roof membrane on 5 inches of rigid insulation. So it just says 5 inches of rigid insulation. What's the R value to 5 inches of rigid insulation? Exactly. Rigid insulation, guess what? Rock wool is considered rigid insulation because they have a form of rock wool that they call their rigid insulation. So we got rock wool. That only gives us a 4.8. 4.8 times 5 is not 30, right? Rigid insulation could be the styrofoam insulation, right? And that only gets us, what is it, 3.8? Doesn't get us where we need to. Now it could be polyiso. 5 inches of polyiso is going to give us 35, better than 35, which would be a great start, but we don't know. Plus, it shows only one layer. It's required that you have to have a minimum of 2 layers for our rigid or for our above roof deck insulation. So, looking at this image, would you say that it's meeting the requirement that we need for above roof deck insulation? And it does show the R value, but not on this picture. I'll just give you a hint. The R value with the design met the requirement. So take the R value requirement out of the equation.
What is a stagger?
Oh, that's an excellent question. Does the code have a definition of what's staggered?
The manufacturer might.
Ah, there you go. That's where you'd have to go. I think you could use your good judgment and you can see, other than this spot right here where there happens to be a joint, everywhere the staggering was fairly significant. I would say it met the intent that it was staggering its layers. But if I had a question on it, then I would go to the manufacturer's specs. So what about this image? What do y'all think? Would you pass this? Oh, somebody feels very strongly over here. And I'm very happy for you. I like your strong opinion on this because the answer is no. This was not staggered, and it looks like there's a good distance there. There really wasn't. It was a matter of this much, but from the angle that the picture was taken and everything, it looks larger than it was. But the conversation then goes, where does the code say how much it has to be staggered? And it's not in the code, except for if you go into chapter 3. Chapter 3 is probably one of the most neglected chapters in the energy code book because many people think of it as, oh, that just gives me what climate zone. And you're absolutely right, it does give you the climate zone. But section 303 also gives you a whole bunch of really good information, and it is an excellent location for inspectors to know all that's in there, and contractors, honestly, because it tells you things like, hey, the certificate, insulation certificate, that comes out of 303. It also says that all materials, appliances, and equipment must be installed per the manufacturer's installation instructions. So that is a section that you should rely on heavily. All right, let's talk about metal buildings, because metal buildings are not the same as metal framing. Metal buildings have things like girders, purlins, what do I want to say? There was something else that I thought of, but it has that metal skin to it. So it's metal on metal on metal on metal. And so we have to take into account, really when everything is said and done, the amount of thermal bridging that you're going to get from a true metal building compared to maybe some of the other building types out there. So we're going to get through the roof section. Then I'm going to give you guys a break. So just so you know, it's coming up here. All right, so let's talk about what the table has for us for metal buildings. So here are 5, 6, 7, and what Aspen has, because Aspen, I believe, did amend this, or maybe they didn't. Now I can't remember. But the big thing is, I want everybody, whenever you look at a table, most people just skim over that idea of the footnote, and they don't think about it. That footnote is either your friend or your foe. And when I say it's either your friend or your foe, friend is because you looked at it, because a lot of times there's flexibility built into it. If you look at that footnote, the other thing is it becomes your foe because you didn't follow that footnote and you did something that now kicks you into a whole different area, which is what happens here. If you do not include in your roof assembly for metal buildings a thermal spacer or thermal break, you cannot utilize the R value table. You have to then go to the U factor, C factor, F factor table, which is your assembly approach, which means you're not just putting insulation in there. Now you're providing documentation of each assembly component, telling me where you got the R values, doing all the calculations, and it's sometimes just a lot easier just to put that thermal spacer in. But it is something to be aware of. So here's an example of on a set of plans where they demonstrated that we have that thermal spacer involved. Now, there is a difference about metal buildings and how they are shown within the table. Yes, this says climate zone 3, but we don't care what climate zone it is. It's really, we're going to discuss the design that they're calling out here. So on this, it says an R19 plus an R11 LS. What's an LS? Liner system. Exactly. So now we have a liner system. The Energy Code does provide a definition as to what a liner system is. That liner system consists of having a vapor retarder underneath the purlins. So we have a vapor retarder under the purlins. Then we have insulation placed between the purlins on top of the vapor retarder. And then we have insulation laying across the purlins, going perpendicular to the other insulation installation. And that all together creates a liner system. So we have the R19. That R19, that first number, is the number that goes in between the purlins. The R11 LS is the insulation that goes over the purlins and over the thermal. So looking at the installation here, would you say that, I know you can't see everything, but from the angle that you get to see here, does this meet the intent of what is required for the design of that metal building roof? Yeah, they did a good job. The vapor retarder here is located below the purlins. Yes.
So in the majority of these buildings, you're going to see fire separation occupancies along the length of a 150-foot building. And in our experience, especially in the local counties, that the fire separation wall is going to go up and compress the insulation up against the metal decking, up against the thermal break. And it's also going to either cut or compress the liner system. Either one of those are addressed in the code, and the building officials seem to struggle with that. One violation of the fire code for the fire separation wall going cleanly to the metal deck, and being fire safe or caulked, and then the compression and lack of insulation above the firewall.
I'm glad you brought that up, because the Energy Code does address that concept. And what there is, if you go into Chapter 1, as long as the jurisdiction has not amended out Chapter 1, which unfortunately a lot of jurisdictions have done in the past, but Chapter 1 basically says, there's a section in there that says the Energy Code cannot impede safety, health, welfare requirements. That fire separating wall meets that requirement, or that situation. So we want that firewall there, because what good is a building where everybody dies and, but we didn't compress that insulation? It's basically they're saying, okay, so if you have this tiny little section that you do have to separate with a firewall, and it has to go all the way up. We know that the continuity has to be there to meet the requirement of a firewall. Then you do your best to ensure that you're doing what you can from here on, but this little sliver is going to have to meet the requirement of the fire separation. And on top of that, typically those assemblies do have insulation that is going all the way up. So you still are kind of, in a roundabout way getting there. Well, there's a big difference. Like I said, I fell into this realm, we're getting close to a couple of decades ago. I've had a lot of experience with this. So my experience with this, plays into how I'm going to answer that. A lot of code officials have not spent as long as I have in the energy world, and they're figuring out where is my balance in how to navigate that. So they're just figuring out the balance on that. What about this one? Does that answer your question? I'm so sorry.
Well, it answers my question.
Okay.
It's difficult, at least as an architect, to be put in that position where then the building official doesn't accept those types of analysis, even though in reality the architect is the one stamping drawings for life safety compliance to begin with. So that we just have buildings delayed for months to argue over simple things such as fire safety. In metal buildings.
Well, here's a great opportunity. Do you provide a code analysis for your projects? Does your code analysis include energy items?
Does my code analysis include? I don't know how to, I would say no.
And that's not uncommon, although it's becoming more and more prevalent. But this is where you have the opportunity, because the idea of that code analysis is really trying to kind of provide a snapshot of how this project meets various components of the code. And this would be one of those times that you could include that type of information on you do your building and do one for energy, and maybe put it in both locations that says, yes, my firewall has to go all the way to the ceiling, and it is going to impede with the liner system, but the remainder of the area is meeting the liner system.
Yeah, we provide those details. I mean, we'll get into the nitty-gritty, but we provide those details of either compressing or continuing the vapor barrier, or tying the vapor in the wall, insulating the entire separation wall, all that type of information. But it's just not, because it's so directed that it is a continuous insulation, and you lose that rating because it's compressed, the argument ensues.
And I think maybe what might be beneficial, because and I'm just assuming, obviously I don't know, but when it's placed in the building side, they're looking at it, okay, so this is meeting the requirement that we have in Chapter 7. Whereas then they have to look at it again, and they're looking at it from what the energy code is. So if you provided, I know it might be more work, but something within the an energy code analysis that said, okay, so it is supposed to be there, but we also have to meet the requirements for fire, so this is how we are complying with it.
It's just not, I mean, we put it in our life safety set as well.
Yeah. So sometimes it's sometimes you might have to duplicate a little bit, but I've had the opportunity of having projects that have both a building code analysis and an energy code analysis. And I will tell you, having that energy code analysis does help in some of those questions where I might have to ask that question, as opposed if it's placed on there. I know that you thought about it and this was the solution you came to that. And a lot of times that helps. It also gives the code official something that they can hang their hat on, right? They looked at it, this was our best solution. We're obviously not going to enforce energy over ensuring that people can get out of a building if there's a fire event. And so it's a give and take solution for everyone. All right, you guys have had a little time to study the image on the screen. What do you think? Do you think it meets the code requirement? I see some head shaking. Why are we shaking our head?
Segregated.
Yes. So in this instance, what they did is they wove the vapor retarder up and over the purlins, as opposed to having it underneath the purlins. So in this image, you'll notice the hatching. That's just to keep the vapor retarder up. And in this particular instance, they did still have that hatching that would have taken care of that, but it was just a matter of a misconception of the installation. So they went up and over the purlin. And the reality is, how many of you, before I showed that to you today, even knew that metal buildings had to have the vapor retarder underneath the purlins? So a few of you did. And you know, until sometimes things are shown to you, you may not have thought of anything different, right? You're just trying to ensure you keep that vapor retarder in place because you know the importance of having that vapor retarder there. All right, so if you look at the image on the screen here, you'll notice that it's missing a thermal spacer being called out there. So this, while it says I am installing an R25 with an R11, it can't follow that pathway. It has to now use that U factor, C factor, F factor option and can't go with the R value of the project, which is what they were doing. Even though, no matter which compliance path you have, you still have to put that R value on the plans. So they would have to go and utilize and follow the simple saver system, which is really hard to see on this screen, but they happen to have two designs there that have that R19 plus R11, which most jurisdictions up here would have to follow, or they would go 2511. But the R1911, one has a thermal spacer, one does not have a thermal spacer. So even though that they're using that simple saver system, does not always mean that it meets the requirements of the code. So here's an example of them installing that thermal spacer on top of those purlins. All right, attic insulation, which probably doesn't need a whole lot of explanation about the insulation. You will notice that if you're in climate zone 7 or if you're designing in Aspen, you are required to do an R60. Keep in mind, depending on the type of insulating material you utilize, 1/2-inch gypboard may not be sufficient for the structural integrity. You may have to jump up to a thicker gypboard. But again, it's just dependent on the type of insulation that you're going to utilize and the weight of that insulation. Now, the one thing I do want to talk about when it comes to attic insulation is you cannot rest insulation on top of removable ceiling tiles and count that as part of your thermal envelope. You can have insulation up there, and in fact, you know, if you have an office right next to the restroom, I highly suggest putting insulation in that area, right? Only because I had somebody call and yell about it because she had an office right next to the restroom and she was really tired of hearing her coworker's business. I get it. But otherwise, it does have to be placed in that attic area and not resting on the insulation or on the removable tiles. So, this brings us to the end of the roof, and as I promised, we're going to take a break because I can tell I've given you a lot of information and your brain's ready to explode. So let's go ahead and take a, what time are we at? Is it really 10? Wow. Let's go ahead and take a 10-minute break here, and we'll come back and hit the rest of the thermal envelope. For the amount of insulation that walls, above grade walls, would have to have. Climate zones 5, 6, 7. The last one is Aspen. So as you can see, the insulating values are going to be significantly different. So it will entail a little bit more forethought in how you're going to maybe design these for Aspen. All right, let's talk about the first one. So our first one is dealing with mass walls. What's a mass wall?
Make up a church.
That's a good one, Rick. I have to say that's probably the first time I've ever heard that one. All right, I'm going to use it in the future, somehow, some way. All right, so mass walls. You see that nice little footnote F, or that little connotation of footnote F? Didn't come out well on here, but footnote F sends you to section 402.2.2, which gives us some information about what a mass wall is. So a mass wall has to have a component or that weighs less than 35 pounds per square foot of the wall surface area. I'm going to have to look and see here. The other one is that it weighs not less than 35 pounds, or I'm sorry, not less than 25 pounds per square foot of wall surface area, and has a material weight that is not more than 120 pounds per cubic foot. Number 3 is it has to have a heat capacity exceeding 7 BTUs a square foot. And the other one is have a heat capacity exceeding 5 BTUs with a material weight that's not more than 120 pounds per cubic foot. Does that make sense for everyone? Everybody know exactly what mass wall materials are? Huh. So this is the fun one, right? So as a plans examiner, I have to determine, does this wall meet the specifications of being considered a mass wall? So how do I do that? Have absolutely no idea. Can I look at a design and say, well, if I take the square root of 42 and have fun and jump on one foot, it equates to being a mass wall. So we do have to have that type of information provided to us. A lot of times I have seen it placed on the plans themselves. Example, what we see here that says, hey, this wall is going to be this. Another great location is a comm check is provided. When you go into comm check, you say mass wall, you have to fill out a little bit more information in there. And if it says, hey, it's going to be number 3, it meets the heat capacity. wonderful, I can move on with life, gave me the information, and everything's happy-go-lucky. But what happens if it doesn't meet that specification? Ooh, okay. Think about that for a little bit. We'll move on. Let's talk about our metal buildings. As you can see here, not only do you have to install a cavity insulation, you also have to install a continuous insulation value if you're going with the R value table. So in the instance of what we see here, because you really can't see it, what they provided was just insulation. Now they provided a system for it, that Simple Saver system, and I'm not promoting Simple Saver, it just happens to be a lot of times when I get metal buildings, that's the insulation system that they call out on it. But for the walls, in this instance, it's just one insulation layer. It doesn't meet this, even though this says right here, an R13 plus an R14 continuous. If they were putting an R27 in the cavity, does that count? Does that work? Maybe they'd have to go in and use ComCheck, because even though if you take the numbers 13 plus 14, that does equate to 27, absolutely. But the R14 is continuous insulation. So basically what you would have if you were just installing 27 is you have 27 in the cavity, an R6, 27 in the cavity, R6, because that's the stud R value, potentially, 27. So is that the same as having an R14 continuous insulation that has no interruption from that framing member that assists with the thermal bridging? Continuous insulation, I know lots of people have concerns about continuous insulation, but continuous insulation really does have its place in the thermal envelope, because the reality is in physics, it's not, made up. We have thermal bridging. So how do we address that concept? We install continuous insulation to kind of break that up and keep it from spreading to the other materials surrounding it. So the picture on the right there is just showing insulation was placed in the wall. This particular system, because they didn't go with the R value, they actually went with ComCheck, so they traded some stuff to be able to do that. All right, let's talk about metal framed. Metal framed, as you can see, once again has cavity plus continuous. You'll notice that the cavity of the R13 is very similar to what we saw for a metal building, but the continuous insulation requirement was reduced. If it was a metal building and a metal framed, why would they reduce the continuous insulation amount for a metal framed compared to a metal building? What does a metal building have that a metal framed building wouldn't have? It does have drywall. Probably it might have it for both. But what's the one distinctive feature that a metal building has that a metal framed building isn't going to have? Metal skin. Remember, a metal building, a true metal building, has metal and then metal skin covering it. So we got metal on metal. Whereas typically, as you mentioned, for a metal framed building, you got Den's glass, usually, or maybe OSB or something. But typically in that design, we have Den's glass going on, which is nothing but chipboard sandwiched by, fiberglass mats. So that's why that insulation value is reduced, because there's still thermal bridging, but there's not as much thermal bridging that a metal building will do.
Can you speak a little bit to why? Because you would expect a metal building more conductive, right? Like thermal bridging to happen more easily. Can you speak a little bit to why it
Why a metal framed building
Why
wouldn't?
a metal skinned building would actually end up requiring less insulation.
Oh, no, no, no. The metal skin building has to have more insulation. So, yeah, so this is our metal building. It has, we'll just look at 6 where it has R13 plus an R14 continuous. Sorry if I said it backwards. But the metal framed building has a requirement for less continuous insulation. Thank you for bringing that to my attention there. So here's some examples in a metal framed building where they did cavity and continuous. This is where they actually installed it. They did a really good job with this one. I love the way that they did it. Of course, I was the inspector going out for it in my jurisdiction, so they know what I expect. They know that I inspect to what I expect. So anyway, wood framed and other. What would be an other for a above grade wall?
Block wall.
Block wall. What else? Straw. How about walls that don't qualify as a mass wall, which you kind of alluded to up there? So if a mass wall, what you would consider typically to be a mass wall, doesn't fall under one of those 4 categories, it can't meet it, now it's kicked over to here. And so now it's considered an other wall. So in these instances, you're doing a cavity plus continuous for all of those. You just have various degrees of the amount of cavity and the amount of continuous that you're going to install. So here's one that I want to bring to your attention. It's one of my favorite ones to talk about. So here's the example here. It's really hard to read, but it is a 2x6. It calls out that we're going to have an R20 insulation. Works out well. This one down here, it says we're going to have an R21 fiberglass insulation. It's also going to have 3/4 of an inch of continuous insulation, which gives us an R3.8 for that design. Are we okay with that? Potentially. Here's where it becomes a problem. Right here, it tells me that as an optional replacement of rigid insulation, you can have OSB and house wrap with zip panel. Are we okay with that option? Or did we just reduce the thermal envelope? Potentially. It's really dependent on the zip panel. Is the zip panel a insulated zip panel? Because they have R3, R6, R9, right? So it could be somewhat of a fair trade if they're going with the R6, but not if it's an R3, because 3 is less than 3.8. It's not a fair trade of an option. You still have to ensure that that continuous insulation is going to meet whatever it was designed for. So in this particular option, there's a potential that that continuous insulation goes away. What happens when we don't have a thermal envelope installed the way it had been called out on the plans out in the field? Oh, go ahead.
Is your major issue with that just that they don't specify the dimension of the zip panel? Because they were to replace the insulation, the OSB, and the house wrap with the zip panel. As long as it said 1.5 inch zip panel on there, it would be actually more than what is in that assembly.
If that zip panel called out that it was an insulated zip panel, that's what I need. I need to know that there's still going to be continuous insulation in here. Because in the original design, they called out that they're going to do 3/4 inch continuous insulation, which equates to that 3.8. When you remove that 3.8 of the continuous insulation by doing the OSB zip panel or OSB and house wrap with a zip panel, then I need to know, that that continuous insulation is still going to be in place. And so part of the reason and the ramifications for that is the thermal envelope and the building as a whole is not just a whole bunch of little components living all on their own. There are a whole bunch of little components that work together for a bigger picture. When you remove that continuous insulation from that thermal envelope design, on the mechanical side of things, the mechanical equipment, they did their heating and cooling load calculations to ensure that they got the correct sized equipment out there so that it's performing properly. If you remove that continuous insulation from the equation, now that equipment, I can guarantee, is probably undersized to be able to handle the heating and cooling loads that are happening within that structure. So we have to make sure that we're giving it apples to apples. Even if it's an apple and a crab apple, we have to ensure whatever options are out there are comparable to what we need to ensure that the system is basically the same here. Now, I always bring this one up here, and it doesn't necessarily apply too much here, but if there was a requirement that you could have an R20 cavity all on its own and you install an R19, does that meet code? It does not. That was a common practice because everyone said, oh, it's only one R value less, and you're right. That math checks out. Even I know that math checks out. But the reality is the code states if you're going with that R value option, you cannot do anything less than what is listed in that table, and an R19 is less than an R20 in there. All right, so below grade walls. Below grade walls, and I just noticed I had a fat finger in there. To be considered a below grade wall, it's actually 80%, not 85. Sorry, my finger must have slipped there. But basically, if 80% of the wall is below grade, that wall is then considered to be below grade. Otherwise, it's an above grade wall and you have to follow the requirements out of that previous lines of the table. Now, the other thing that's really nice, if you happen to have a below grade wall and the walls happen to be, 14 feet in height, technically all you have to do with that continuous insulation is go for 10 feet. So you could, in theory, leave the bottom 4 feet without insulation because you're only required to do to a minimum of 10 feet or to the lowest floor of the conditioned space. So here's an example. How many of you get below grade walls for commercial projects? Anyone? Couple? All right. It's not probably as common as we see with residential, right? But I've had really one project in my career that actually qualified as below grade per the definition. And it happened to be this one. So it was the manager's office, which I felt bad for because they were stuck in the basement in this office, no windows, nothing. It was like, we're going to hide you from the light of day. But they did a fairly good job in demonstrating that insulation component. And it was continuous insulation. Now, the installation of it was shown great on the plans. The actual installation of that continuous insulation, we'll just say that there was a drastic room for improvement. Everybody has good things and bad things that, you need to work on. All right, let's talk about floors. How many of you just love the idea of figuring out how to deal with a thermal envelope for floors. How many of you cringe as soon as I said floors and thinking about how to deal with it with the thermal envelope? All right, well then, I think it's wonderful. So if we have mass floors, you're required to have continuous insulation. If you have a joist floor, you are required to have cavity insulation. It also has to be in constant contact with the underside of the floor slab. Now you'll also notice for it to count as a slab or a mass floor, it has to be, the weight of it has to be not less than 35 pounds per square foot, and then it also has to be 25 pounds per square foot and have a material weight that is at least 120 pounds per cubic foot. Now there is an exception for the mass floor, and it does give you a 1-inch gap that is available in that design. So, how do you guys deal with podium construction? What are you guys doing for that? If you're separating an unconditioned garage from the rest of the building, that ceiling floor separation is your thermal envelope. How many of you, now that I said that, want to cringe when I bring up floors? Nobody? I would say floors are one of the areas that is really difficult. Now, there is an option out there for if it's a joist floor. Now, what you are permitted to do is extend the above grade wall into the floor cavity and allow that floor insulation to rest on top of gyp or continuous insulation, whatever the case may be, as long as you extend that wall down into that floor cavity. And the idea is if you don't, then you have that break within the thermal envelope. And so that's why the above grade wall is going to extend down.
Doing that on the inside of that as well is acceptable, right?
Yes, yes. All right, let's talk about our slabs. If you are a unheated slab, and that slab is 24 inches or less above grade, you will then have to insulate your slab from top of slab extending down. Obviously, we're making sure that we still have the continuity of the thermal envelope, but the idea is you're going from top of slab down. You can do it on the interior, the exterior. It's kind of up to you, but the important thing is, taking a look here, is we have to insulate down for the distance. Now, here's the really nice thing, and I guess we'll talk about it in the next slide, but there is a little caveat for that. Now, the other one is if it's a heated slab. Now, not only are you going to insulate the foundation, you're also going to insulate underneath the slab. And it's an R5 for the entirety of the slab. Now, there is a little bit of a clarification that happened in the 24, which states that if you have a heated slab and you happen to have a structural column, the area of where that structural column is, we're not requiring that an R5 has to be there because it's a structural column, right? Makes sense. But apparently there were some concerns with it about the design, so they put it into the 24. Just be aware if it's everywhere underneath that slab, but if you have a structural column, we obviously want that structural column to be there because we like buildings to stay standing. Yes?
What about mechanical components under slab? Are you looking at that to encase the mechanical enclosure or to be above the mechanical enclosure to the slab?
Well, I guess it would really depend on the location of where that mechanical equipment is. Now, are you talking about the equipment running under slab?
Ductwork, supply lines, anything to that effect.
Yeah, so technically how they're referring to it, and this is how, because remember this requirement actually came out of the mechanical code. They moved the requirement from the mechanical code into the energy code to ensure that we had continuity going on there. But how they required it was that it was underneath the slab, because the idea is we want to ensure that that heated slab, the heat is going up and not going down, because hot will always go to the cold. In theory, the cold, it's going to be colder above, but the idea is we're moving it in the correct direction. As far as where the ductwork would lie, I would say most of the time the concern is just ensuring that insulation is directly under the slab and it doesn't have to be underneath that ductwork. Now that ductwork then is considered to be outside the thermal envelope, so then you're addressing it depending on the type of ductwork, whether it's just flat out insulation or you're doing the thermal distribution for it. Yeah. Great question. All right. So it's a requirement if it's 24 inches or less below grade, you have to ensure, obviously, that it's continuous, but that insulation has to start at the top of the slab. It can go above it, and in some instances it obviously does for the design, but the idea is a lot of times when we talk about slab edge insulation, it's often placed below the slab. It can't be placed below the slab because it's not doing what it needs to be doing. So with that, it starts at the top of the slab. It has to extend down for the remaining distance that was listed here, or, this is the great thing on the commercial side of things, is that it says it has to go to the top of the footing. So as long as it does that, you're good. If it's a heated slab, like I mentioned, everything underneath the slab all has to be insulated. And here are some configurations that are accepted. You can have it on the exterior of the slab or the foundation. You can have it on the interior side. This one is always a concern a lot of times for the architects and those designing it. And what we have suggested is a lot of times the structural engineer is saying, hey, we need a control joint there. So you can ask, will having that continuous insulation there work as your control joint? I've seen it work, I've seen it not work, or that the structural engineer says yes, or the structural engineer says no, because sometimes we need that compression going on as opposed to having that little bit of a break. But that's okay, because you can still place it on the exterior side. You can go from top of slab, bottom of slab, and then underneath the slab for the remainder of the distance. You can go on the outside, top of slab, extend down, and then extend away from the foundation. But for whatever part that you extend away has to be covered with at least 10 inches of dirt or concrete. And then the configuration that we have down here is for the heated slab. Goes from top of slab, bottom of slab, and then you have to insulate under the slab. Guess what? They don't ask that if you have a heated slab that you have to do it for the remainder of the distance. Once you get to the bottom of the slab, they're calling it good, because technically your thermal envelope stops underneath the bottom of the slab, right? So you don't have to extend it down further. So here's some examples of where we have slab edge insulation going on. And we also have it here. Here's one where it was a heated slab. So they had the insulation underneath the slab, but they had this insulation extending all the way down to the top of the footing. They technically didn't have to do that. All they had to do was start at the top here, go to the bottom of the slab, and the rest of this didn't have to be there. So it's a great way of being able to maybe cut some costs and use it in a different area of the project.
Can't frost get underneath from the outside? Can it get underneath that slab?
It could,
If you don't
absolutely.
do that vertically, all the way down to the footing? I mean, can't frost still come in underneath?
Well, remember, this is a heated slab.
Right?
And
So can it get underneath?
I suppose it probably could, but the code does allow that all you have to do is go to the bottom of the slab when it's a heated floor.
I think that's a mistake.
It might be, but remember, that's what the code states.
I would agree with that, like, you always have to assume that at some point the owner's going to shut off that heat at some point to be able to insulate it. So, I would keep it vertical.
Nothing says that you can't extend it down, which obviously they did, but technically by the code, as it states, all they had to do was go to the bottom of the slab.
I hear you. I don't agree with that.
I understand. I can convey what the code says. And the idea of that slab edge insulation, right? The idea is we're really trying to deal with condensation, because anytime you have cold and hot, what happens? Think about it on a summer day. You have your nice, cool, iced adult beverage. What happens to the glass? Condensation. It sweats. Yeah, exactly. So it's the same kind of concept that they're trying to address here. So it's not as if your concern isn't valid. It's just that that is not how the code is written currently. All right. So here's one that I get questions about often. How do I address it? Because we can't do that control joint. And so, how do I think about ensuring that I am meeting the requirement for the slab edge? So in this instance, they placed part of their slab edge insulation on the exterior, and then they started their slab edge insulation on the interior right below where the slab is. How many of you would accept this? How many of you would not accept this? How many of you are curious what Hope accepted? I'm going to say I accepted this design. Nothing says that it has to all be on the outside or it has to all be on the inside. It just has to be continuous and maintain that continuity. And this design, in my opinion, does. And then here's an example out in the field, or of this project doing it out in the field.
How do you consider it continuous if on the outside it's just a foot, the inside goes all the way down, and there isn't anything, are you calling the concrete tying them together, the continuous?
Well, see, we have it continuous coming here. We have continuous going here, and they overlap, right? It wasn't like this. They overlapped each other. So in the idea is, a lot of times when you are dealing with different designs, transitioning from one assembly to another assembly, we don't necessarily have the overlap like this, but we accept it, such as when we're going from bottom plate, foundation assembly. We don't have that necessarily insulation in that bottom plate, but we have it going up to it and we have it going in the cavity. And so we accept that. And this again is just how I accepted it, because there's this wonderful word of intent. And I felt that it met the intent of what this section was trying to do. So I would accept that all day long. And I'm sorry, I keep bumping. All right, so what do you guys think about this one? Here's what I'm going to say. In the installation, something that happens all the time when I go out and take a look, what do you see at that corner? You see a gap. Corners are notorious for gaps to happen. And so this is just one of those areas. I could probably pull up, I kid you not, 30 pictures of where I take pictures of gaps at corners. And so it's just one of those areas that when you first look at it, you're like, all right, we got insulation here on this side. We got insulation going on this side, we're good. But this is an area that we need to, everybody has an area that they need to do better with. That's the area I think we could really work on. All right, skylights. So you have to insulate the curb of the skylight. Has to be at least an R5 insulation or what the R value is for the above roof deck, whichever is less. So basically just ensure that you insulate it at least to an R5. Now, skylights are required if you happen to be one of these occupancies. You have a roof height that is at least 15 feet for 75% of the space, and underneath it that space is at least 2,500 square feet. That point, skylights are required. Here's an example. Let me show you all the skylights in this gym cardio area. So they're required to have the 3%, not more than 6%, right? A minimum of 3%. For this project, they had one in the men's locker room, one in the women's locker room, and then I think the remainder of the skylights in this very large gym, probably I think it was like 11,000 square feet, all resided in the cardio weight room location. So a lot of natural light to highlight all the efforts of pumping iron, I guess. All right, let's talk about our glazing. We kind of transitioned there. So our fenestration. Our fenestration has some very distinct requirements. As you can see, here's our requirements if you're just going out of the 21. Here's the requirements if you are working in Aspen. You'll notice that the R values are significantly reduced not the R value, sorry, the U factors and solar heat gain coefficient are significantly reduced within Aspen's amendments. Now, let's take a look at the solar heat gain coefficient, because in this table, it is broken up by whether you're a fixed window, an operable window, or you happen to be an entrance door as far as your U factor. When it comes to the solar heat gain coefficient requirement, it's based off of, are you fixed, are you operable, and then it's also listed by your PF. What's PF? Yes, Rick, gold star for you, projection factor. So how do we know what the projection factor is?
The manufacturer does.
Nope. How you determine the solar heat gain or the projection factor, I hope I put it in here, I did, is basically you're taking H, divide it by V, and H is determined from taking the glazing, the fenestration, and measuring the distance to the edge of the overhang. That gives us our H. Our V is measured from the bottom of the fenestration to the underside of the overhang, and that gives us our V. So if we take H, divide by V, that gives us what our projection factor is. So we all have phones. What if our H is 15 and our V is 66? What's our projection factor? Yep. We're at 0.227, something like that. So it could be 0.22, 0.23. There's nothing in there that says it's got to be rounded to the next whole number. So in my opinion, if you said it was a 0.22, I'd call it good. If you said it was 0.23, I'd also call that good. Now, with the projection factor, that takes us back here to which line we would look at. So in here, since it's greater than 0.2 but less than 0.5, this is the maximum solar heat gain coefficient for each window. But here's where it gets to be a lot more fun. In this design, our projection factor for this window is going to be different than what our projection factor is for the floor above. How many of you just said, oh, I hate you, Hope? It's okay. I got broad shoulders. I'll take it. So how this is often addressed, instead of doing all of the math and saying this window has to be a 0.36 and this window has to be, down here a 0.33, typically what I see on the plans is they'll call out and say, hey, all windows will have a maximum solar heat gain coefficient of 0.33 because that's the most restrictive value in there. And so if everything has that, then all that means is you might have windows that meet what's in this table, and then you might have a few windows that are a little bit better than what's in that table. But it also helps that you don't have to do all that math for every window on every story on every floor, right? So, all right. The next thing is we're required to get an NFRC certificate. When are NFRC certificates issued for glazing? When you buy the window. Have windows been bought before the plans are approved and the permit is issued? Well, okay, sometimes, but not typically. Typically, architects and designers know that there might have been something that was missed. There's an egress window that didn't think about and you missed, so you got to change things up. And so typically, they're not bought before the permit is issued. So how do we as plans examiners ensure that the glazing's meeting that U factor and solar heat gain coefficient?
Check the labels when we do the rough framing inspection.
When you go out to do inspections, but for plan review to get it issued, do you just hope it's okay? So here's my suggestion, because otherwise we're kind of running on this hamster wheel, is the fact that what we do is we take the framing manufacturer's compliance certificate and use that to demonstrate compliance. Like, hey, they're going to meet this because those framing manufacturers have it down. So if they say the U factor is going to be, 0.32, then you can look at this and get an idea of what that would be. So this is the U factor at center of glass. You'll always get the center of glass and then you'll get the overall assembly U factor. You need to be looking at the overall assembly U factor. So in this instance, we would look in this row to ensure that the windows that are being called out actually meet that requirement. And then, as Derek mentioned, I'm going to take that NFRC certificate and take a look at the lovely non-easily rateable ticket that's left on that window, because it's not like our residential windows that say, hey, I'm a U factor of this and I'm a solar heat gain coefficient of this. We get to take this, try to decipher which number am I looking at to find it on the NFRC certificate to say, oh yeah, that is a 0.38. Oh yeah, that is what the plans say. So that's the fun of it. All right, the most dreaded section, new section of the 21, I think, is the air barrier section, because it used to be the choice of you can either go prescriptive, which is follow all of these requirements and we'll call it good, or you can do blower door testing. In the 21, basically, unless you fall under one of the few exceptions, all projects are going to have a blower door test performed. And I would say buckle in and get really good at it, because those numbers in the 24 get reduced significantly. So practice makes perfect. So you can have your air barrier on the interior, on the exterior, a combination thereof. Whatever it is, it has to be continuous. And it's not just the walls that are required to have air barriers. The roof, anywhere the location of the insulation and the thermal envelope resides, you have to have an air barrier there. All right, so the very first one here, it says, well, I want to talk about this one right here. It says you got to comply with C402.5.1.1 and C402.5.1.2. We're going to skip 1 and go directly to 2, and then we'll come back to 1. 2 says, hey, if you're a Group R or Group I occupancy, you're going to comply with C402.5.2. 402.5.2 tells us that you're going to be doing blower door testing if you're a dwelling or sleeping unit. You're going to ensure that you do not have an air leakage rate that exceeds 0.30 CFM per square foot. Now, that metric is a much better testing metric than air changes per hour. Air changes per hour is heavily predominant on volume. When we're looking at this, this is typically like an apartment, multifamily, sleeping units, things of that nature. So you don't have the volume with it, and the CFM per square foot is a much more neutral metric to utilize for it. You do have to ensure that you're not exceeding that number. Now, here's the nice thing. It doesn't say that you have to test every single unit, unless you have 7 units or less. If you're 7 units or less, then you're testing everything. If you have 8 or more, you only have to test 7 of your units or 20%. Once 20% equals that it's more than 7, then you're following the 20% on that. Now, what it also says is that it has to be an unguarded test, and I'll talk about what an unguarded test is here in just a moment. But it gives us parameters as to what type of units are going to have to go on test. You have to have a unit on the top floor. You have to have a unit that's on the ground floor. You have to have the largest unit available tested. And then any of the other ones is just basically dealer's choice. Whatever the contractor chooses. It doesn't matter what the inspector doesn't get to say, I want this unit, and this unit, unless there's some sort of policy on there. It's really the contractor's choice. But for every unit that fails, you will have to test 2 more units. So you do want to ensure that you are paying attention to your air barrier assemblies, because it can get rather expensive pretty quickly as they start building up. Now, I mentioned an unguarded blower door test. Basically what it means is it's a single unit that goes on test. If it was a guarded blower door test for this middle unit, you would put all the units that touches that unit on test. So it's not a true representation of how leaky that one unit is. The code is saying, no, 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 no. We want to know how leaky that one unit is. And that's why it has to test all on its own. All right, let's talk about number 2, which is anything that isn't a Group R or Group I occupancy. Now you're complying with C402.5.3. So let's see what that section has for us. This section has different testing standards than what we saw because it's dealing with a different type of concept for it. It says in this one that you cannot exceed 0.4 CFM per square foot. Now, the difference between the residential, you're like, well, residential is 0.3. Isn't that less, more restrictive than 0.4? And you have to think of it, it's not exactly apples to crab apples here, because residentially, the Group R and Group I's only had to do it to 50 pascals. Those that aren't Group R and Group I have to do it to 75 pascals. So that's one of the difference on that. You also get to do like an area weighted average, because we might have, I think we've all had those, right? 50,000 square foot buildings. And so it's going to allow you to do the area weighted average. Now there are, yes.
Oh, I'm sorry.
Oh, no, go ahead.
On your last slide, we had a project at multiple hundred units, and the unguarded test came back that the inspector required the adjacent units to have doors and windows open.
Well, here's a great thing. So in this particular instance, they have to test it to the testing procedures out of ASTM E779, ANSI, ResNet, ICC 380, which is pretty much what we're used to residentially, or ASTM E1827. So whatever those testing procedures require is how they have to test. The inspector can't say to the contrary because the code says you have to do it per this. And if the testing metric says, or procedure says, yes, those doors have to be open, then you would have to. But if it's not addressed in those testing procedures, you have to follow what these standards require. Yeah, so that's what you have to follow. That's what is required to be followed. Unless there's some other amendment that they've instituted in their adoption. Otherwise, what you're doing is following this. All right, so for the anything other than a group R, group I, that one, what you have to do as far as the testing requirements, anything that is under a roof is required to go on test. So sometimes we might have a 3-story and then an offshoot that's only 2 stories. Both of those top units or top areas are going to be required to go under test because they're both under a roof assembly. A story that has a building entrance, any exposed floors, loading docks, or if you have anything that's below grade, that's going to be required to go on test. And then 25% of that remaining area will have to go under test. And then again, that is kind of dealer's choice as to where you're going to do the 25% of it. Now, just in case you end up exceeding that 0.4 CFM number, as long as it's not more than 0.6 CFM, they're kind of giving you a prescriptive version of a fix for it. And so what it says is what you're going to do is you're going to put it on test. You can use infrared, you can use a smoke tracer. You're going to go around, see where the leaks are, fix them without doing deconstruction for it. Then what you're going to do is provide a report saying, hey, we had an issue here. This is how we fixed it, and provide it to the building owner and to the building official. Make sense? Now, the third option is if you happen to fall under, you don't fall under the 1 or the 2, now what you're going to do is comply with 402.5.15, which is basically you're doing thermal envelope commissioning. So what you're going to do is you're going to either have the building department, the building official can do it. You can have a registered design professional or an approved agency. Obviously, somebody not associated with the project. What they're going to do is review the plans. They're going to document the issues that were found on the plans, how they were corrected for the air barriers. Then they're going to go out into the field, do periodic inspections of the air barrier. They're going to write up any issues that they found out in the field, how they were corrected. At the end of the project, a report is going to be provided to the building owner and the building official that states, here's where the deficiencies were, here's how they were corrected. So now what we're going to talk about is the part that basically everybody's going to do. It's the prescriptive items. These are all the things that are not new. We've had them in there forever and a day, so we'll go through them. Basically, we have to ensure that our air barrier is continuous. We have to take into account that we know we're going to have joints and seams. We've got to seal all those up. We have to ensure that whatever material there is is secured and is going to stay secured and take into account things like wind, stack effect, ventilation, and all of that. Now, number 3 here talks about sealing up penetrations. We got to make sure that whatever material is utilized is suitable and compatible with what it is trying to kind of seal up. So the instance here is, you know, in those penetrations, you aren't going to use packing tape, right? Because packing tape is not suitable for the material and the location. And you say, Hope, that's an odd statement. Why would you pick on packing tape? Because the reality is I've gone out and seen packing tape utilized to seal up a penetration. So unfortunately, it happens. And whatever it is, you have to ensure that it has the capability, again, of dealing with stack effect, negative pressure, wind, the mechanical ventilation or vibration. So in this particular picture, they had a really good design. This is a multifamily. It was 21 stories, had this issue on all 4 sides of the structure. You'll notice here, we got a penetration with a flashing system. Then we got a flashing system, no penetration, and then a penetration, no flashing system. What happened there?
Oops. Is that window operable?
Oh, there you go. That window is operable. So on the plans, it was all good. It was measured out. Everything was fine. Construction is not always perfect, right? Best laid plans on the plans, but when you get out there, that, you know, joist was in the wrong spot or a different spot. So the distance from that operable window did not allow for that penetration to be there. It had to move over to the next space. So now what you have to figure out is how are you going to seal that up, and what are you going to do with this big opening? Because do you think if, you know, siding went over there and they did their blower door testing, it would pass? It would not, right? And the reality is, remember, I said that this was 21 stories. This was the issue on each story in multiple locations and on all 4 sides. So that is a lot, and I can guarantee you if they left it, it would not have passed the blower door test. Just throwing it out there. What do you guys think? Good job? So this was, I was at a drive-through, right? They had just done, redid this whole wall deal due to a natural disaster, right? So it was supposed to be sealed up. I jump out of the car. The person driving is like, you got to stop jumping out of the car for pictures. You're freaking me out. But I see this and I take a picture. You could look through and see the other side. So not only was it not sealed, this is an exterior wall, no insulation in there either. So that was a fun one. Another one to be aware of that I see all the time that it is not sealed up are penetrations going through CMU walls. Just because it goes through a CMU wall does not mean it's exempt from having to be sealed. It still has to be sealed. You still have to use a material that's suitable for it, but it does have to be sealed.
Plus you got galvanic action there.
You do.
Steel.
You do. That's why you have to have something compatible.
Yep.
Packing tape might be a good solution to that. Just kidding.
Do you usually get like manufacturer's specs to confirm if something is compatible? Is that how you guys are doing that, or?
Do you want to know how I do it?
Sure.
Okay. So what I do, it's really dependent, obviously, on the project. I will require that they specify what they're going to utilize. And just through experience, because I've been given all of that information in the past, I can see a material and say, oh, okay, I remember that from this project. It was permitted, so it would work with that. So as a whole, for a lot of, just kind of starting to get that information, I think it's a wonderful idea to have that manufacturer spec on there that says, hey, it will work for this material in this condition. And then you start building kind of like that library where you have that experience too to know this will work with this. All right, recessed lighting. Oh, sorry, concealed sprinklers. Concealed sprinklers are required to be sealed. They just have to be sealed per the manufacturer's installation instructions. How many of you have received the installation instructions for air sealing from the fire sprinkler manufacturer? That's because this has been a requirement in the code since the 2015 edition. When this was placed into the code, the question from me, because I worked with the proponent that put this in, is how many manufacturers have this information? And he goes, well, none, but if it's in the code, they'll be required to provide that information for everyone. I said, okay, great. That same person, every single time I see him, and sometimes he just shoots me an email every once in a while, the manufacturers still have not provided that, because guess what? Nobody is asking the manufacturers for that information. So what they tell Eric all the time is, why am I going to do extra work? If they're not asking for it, why do I need to do it? So I'm going to say, start asking for it. They'll start doing it if people start asking for it. Recessed lighting, we're just making sure we're sealing up, you know, from the housing to wherever it's connecting, because recessed lighting can be anywhere. We do have to ensure that it's IC rated. It can't leak more than the 2 CFM at 75 pascals. And then again, like I said, we're just sealing it up. Now, the Energy Code does have materials that are already deemed to comply. They demonstrate that they do not exceed 0.004 CFM per square foot at 75 pascals. And so the 16 items, we're going to go over them really quick. OSB, plywood. Remember, if you call these out as your air barrier materials, all of these, remember they have to be sealed. All the joints and seams have to be sealed. Extruded polystyrene. This is one material that can take care of multiple requirements out of the code. It can be your air barrier, it can be your continuous insulation. A lot of them are permitted to be your water resistant barrier, so you really could, and part of your vapor retarder strategy. So one material can often take care of multiple requirements, and there's a plethora of materials out there that fall under that category. Foiled face polyiso, that can also be an air barrier. Open cell spray foam, as long as it's 4.5 inches. Closed cell spray foam, as long as it's 1.5 inches. And then our gypboard or cement board. It can be, our gypboard can be on the interior, the exterior. All we have to have is at least 1/2 inch of it to qualify as an air barrier. Then we have our 3 roofing materials. Now, the reason why we have 2 11s here is I just wanted to illustrate that things did shift a little bit in the 21. Before it had to be fully adhered single ply, and now it just has to be single ply. So it doesn't have to be fully adhered anymore. So Portland cement sand purge. We also have cast in place and precast concrete. That's how they meet the requirement of an air barrier. Fully grouted concrete block. Sheet steel or aluminum. This is how metal buildings have an air barrier. Their metal skin is their air barrier. So those are our 16 items that are already deemed to comply. And then we have 3 assemblies. Now an assembly just has to demonstrate that they don't exceed 0.04 CFM. At that point, then they're deemed to comply as potentially being an air barrier. So as you can see, we got 3 options here for air barriers. I'd say stucco, probably not, probably one that I'm seeing more and more being called out as an air barrier. So out of those items that I listed, what materials have you seen out in the field called out as an air barrier that was not listed? So I have had this conversation about the water resistive barrier. Now water resistive barriers, the house wrap, Tyvek, for I guess, product name one out there, could potentially be an air barrier. They have to demonstrate that they do not exceed 0.004 CFM per foot. Well, they have been tested. Some of them have been tested to meet that qualification. The reality is you have to install it the way it had been tested. Most of the time it'll say you only need a 6-inch overlap if it's being installed as a water-resistive barrier. But if it's going to be installed as an air barrier, it now goes from that 6-inch to 18 inches. There isn't, I have yet to see material, and I haven't looked in quite some time, but I have yet to see the material of where for a water-resistive barrier, Tyvek for house wrap, whatever, that has the same installation requirements for a water-resistive barrier as a air barrier. So there are, as far as I know, there are still instances of that out there. What about Den's glass? Den's glass is often called out as your exterior sheathing for commercial buildings. Is it an air barrier? All right, let's talk about it. If it's mud and taped, absolutely. Now you'll notice that Den's glass and those types of assemblies, materials, all they are is a 1/2-inch chipboard or 5/8 chipboard with a fiberglass mat on both sides. Remember, in that table are items that are already deemed to comply. Number 7 says interior or exterior chipboard as long as it's a 1/2-inch. So Den's glass qualifies for it. Now on the screen here, we have materials that are deemed to already comply, but it's not called out as to what the air barrier is. So one material that could potentially be an air barrier is this non-permeable air and vapor barrier. Now the terminology in there is incorrect. It's not a vapor barrier. Are we talking about a water-resistive barrier or a vapor retarder? Because a vapor retarder is required on the interior side of exterior walls and not on the exterior side. So the terminology is wrong. So that becomes a question. The other one is we have 3 inches of foiled face polyiso insulation. That's a material already deemed to comply. We have our chipboard on the interior. We also have our chipboard on the exterior. So we potentially have 4 items on there that could potentially be our air barrier. And which one are we paying attention to ensure that it's sealed? That's what we need to get. And I would say for the architects in the room, get very familiar about calling this out, because when the 24 gets adopted, they have a brand new section that basically gives you a list this long of things that have to be called out on the plans. It can't be placed in the spec book. It is specific, and the amount of information and details that have to happen now are pretty significant. So I would say start now, since everybody's getting ready to look at 24.
Is that still in
103.2, or actually in the 24, it's 105.2. It does list air barrier materials, and it calls out, all of that. But in 406.2, the new air barrier section, that's where it gets incredibly explicit as to all the items that you will put on the construction plans. So here's one. This building is going to be tested. Do you think this is a good one for air barriers? I even helped you out. Look at all the red arrows. My favorite is, so we got OSB. This very distinct black line was a huge gap. So if it was going to be the OSB one, it's not sealed up at all. Plus, I know it's really hard to see down here, but you see this house wrap right here? This house wrap had no OSB behind it. They were just putting the house wrap or the building wrap in front of the studs there. So you couldn't necessarily use that OSB. So the OSB isn't it. Is it the house wrap? The house wrap could be it. But there's a lot of continuity issues. We got penetrations, how it's meeting all the joints and seams isn't correct. And don't forget, there's a big area that often gets missed, is that junction between the wall and the roof. You still have to maintain the continuity of that air barrier there. So what about this design? You guys think that they did a good job? I know it's kind of hard to see, but they did seal up all the joints and seams. How many of you say that I call it good? Raise your hand. I'm going to say it is sealed. It doesn't show up real well on the screen, but you can see where it's a slightly lighter color. No. They used the correct material on it. How many of you say it's not good? How many of you aren't sure and would like hope to say whether she accepted it or not? Right here or right here? That's just the joints where the two pieces are coming together. And the lighter discolorization there is the sealing material on it. So all the joints and seams were sealed. And if you looked at it, you would probably say, hey, you know what, they didn't do too bad of a job. And then Hope gets on there and says, you fail. And you're like, why does it fail, Hope? Because if you notice right here, they didn't seal up that penetration. And if you look at it, it looks like it's just part of that logo, right? And it is part of the logo, so the darkness just looks like it's part of that logo as opposed to they just missed it. So that was just one of those inadvertent, you look at it, and you're looking at it, you know, all day, every day type of deal. You might not see it, and then here comes Hope that says you fail, and you're like, why do I fail? We sealed up all the joints and seams. You just missed this one spot right there. Oh, right down under here? Yeah, that's not sealed. Well, we weren't doing a full inspection.
Okay.
We do partials on occasion. This was a very big project. But this is what Hope called out. What about this one? What do you guys think? This is an excellent one. They sealed that junction right here between that wall and roof assembly. What about this one? What do you guys say?
What's the roof dangling up there?
Yeah, that's their roofing membrane because it's going up and over the parapet. They're using that roofing membrane as their roof air barrier. Right here? Well, the brick there is our exterior cladding. So yes. So it would be technically what they called out was their continuous insulation, sealed up all the joints and seams, but here's where it becomes sometimes you're looking at it and you don't really think about it because they did a great job everywhere else. Right here, there's a break because they're having an architectural feature right there, which was just like a piece of metal. That break voided out it being continuous insulation, because if it was continuous insulation, you can't have any break in it from framing members. That's a framing member. It also voided out that concept of the continuous air barrier because we have a break right there. So I was walking, well, not walking, I was driving by this project several times a week for months. They were doing a really good job. I was driving, on this instance, I was not driving. I was the passenger. Somebody was driving me. I got out my good camera because I noticed, as I was driving down the highway, is that they were missing a spot right here. They did such a good job. You'll notice how well they're sealing up all their joints and seams with their dense glass. They missed one little section right there. and so I had to take a picture of it. And I typically don't show pictures if I know somebody's going to be from that location in there, you know, just out of respect for everyone. I was at EduCode. I forgot in Colorado that jurisdictions send half their people at EduCode and half the people to the Colorado chapters, Ed Institute, so they always have coverage. So I'm at EduCode, I'm showing this. I had the gentleman there, not going to say his name. He goes, I think that's my project. And I'm like, it's not your project. And I'm continuing on, and he goes, no, I'm pretty sure that's my project. And I'm like, no, it's not your project. I'm talking about it, and he goes, is it at XYZ? And I'm like, yes. He goes, we annexed that in last year. Okay, it's your project. And he goes, can you send me that picture? And I'm like, yeah, sure. But anyway, there's some sections that support it. We have to make sure that our fenestration doesn't leak. Here's a table. The table hasn't changed in I don't know how long. I don't even remember the last time those numbers changed. But if water can get in, air can get in. That's why there's that testing that happens on those site-built windows. Doors that are leading to the chutes, elevators, stairwells, all of those have to be sealed, have weather stripping to them. We have to ensure we've done all this work on our air barriers and our thermal envelope, and then we put these big, enormous openings for air intakes and exhaust, which we should. But now we're just saying, hey, throw a damper on that to ensure that we're doing something good. Cargo docks, we got to make sure that we put something that's going to limit the amount of air that happens at the top and the sides when the vehicles are backed in and those doors are open so that products can come in and out, right? Vestibules. Vestibules are required when you have an entrance. Unless you fall into one of the exceptions in those vestibule doors, have to ensure that this one opens and this one isn't open in theory. Unless you have people coming, crossing at the same time, then those doors are going to be open at the same time. And you're not required to have a vestibule at a revolving door, but we are required by code to have a side door next to that revolving door, so ensure that that side door has a vestibule with it. There are some exceptions. Here's some exceptions to it. Air curtains, you can use an air curtain instead of a vestibule. That actually came into the 2015 because until the 2015, if you were an existing building, you had to comply with the full extent of the code, except for a couple of exceptions. So the idea was, let's not make them have to have a vestibule because it's not always conducive when you already have a constructed building. Let's say that they can use an air curtain. At the same time, in the 2015 Chapter 5 came about. This has never been removed, so air curtains are still accepted. Here's some examples of vestibules. Here's one to be aware of. So most people would think about these doors having to comply, but guess what? This door and this door within that vestibule also has to comply with it. The other thing is we have a lot of big, giant doors or walls of windows that open up to let the outside inside. You can do that. You just have to ensure basically that you have interlocking controls, that when those doors are open, that the set point for the temperature changes inside so that you're only heating to 90, or you're only cooling to 90 degrees and heating to 50 degrees, unless you have it zoned. And there's an exception for those areas where they're cooking the food. We don't want the chefs and the cooks and everybody to pass out from heat exhaustion. So those areas can have different temperatures as long as they're zoned separately. So that takes us through all of the commercial. Let's go ahead and take like a 5-minute break so everybody can feel charged, because we're going to hit the residential section. And I promise you, we're doing good on time. We'll get through it all. Talk about residential energy and the thermal envelope. So just like on the commercial side, we do need to have an understanding of what compliance path was utilized for the residential projects. And again, if they go prescriptive, you have the U factor, you have the R value, then you have total UA. Now, total UA is, gives you the opportunity that you can use ResCheck. ResCheck is a free software. RemRate and Ecotrope also do provide the ability to demonstrate total UA with it, but usually it's really dependent on who is producing the documents. If it's an energy rater or an energy consultant, a lot of times they'll utilize the software that they're familiar with, and since a lot of times they are doing, they're involved if they're going ERI or performance path, total building performance, then they're utilizing Ecotrope or RemRate, so you may see that being supplied for the total UA. If it's being done by the architect or designer or builder, often you'll get reports, or it'll be utilizing ResCheck for it. Because again, it's a free software and it's fairly I would say it's very user-friendly. All right. Now, there are some amendments that we're going to talk about. And in this particular instance, for Pitkin County, they deleted section 401.2.4 to create their own. They removed the idea of a tropical climate zone because unfortunately here in Colorado, we do not have a tropical climate zone no matter how much we wish for it. So their new section of 402 or 401.2.4 states that all residential dwelling units will be required to comply with R407. And they added R407.1, which is existing residential buildings shall comply with Chapter 5. New residential buildings shall comply with 402, 403, 404, and 407. And all new dwelling units will be categorized into tiers by floor area as defined by Chapter 5 of the Pitkin County Land Use. And the exception says that this does not apply to accessory structures. Now, 407.2 basically says that you are going to demonstrate that you are going to get an ERI score, and that your ERI score has to be equal to or less than the value that you find in table 407.2. And here is table 407.2. And I know it's really hard to read, but I had to cut and paste because it wouldn't let me put it into a table, so I couldn't blow up the verbiage and everything on it. So basically, it's determined by your fuel source. So if you have an all-electric building, you're going to follow the first row. If you have a fossil fuel or hybrid system in your design, then you're going to follow the second row. The first row says, depending on the size of the structure, if you go from 0 to 3,250 square feet, you have to get a ERI score of 50. If you are 3,251 to 5,750 square feet, you now have to get a 50/15, meaning you get a 50 before solar is installed, and then when you have put your solar on, you have to demonstrate then that your ERI score is 15. And if your home is 5,751 to 9,250 square feet, now you're getting the base where it's 50, and then you're going to show 0 when solar's put on. And I'll be quite honest with you, in this particular instance, there's not a lot of changes for if you have fossil fuel, other than if you do have a smaller home, where in the all-electric you only had to get a 50 ERI. Now it says you have to get a 50 ERI, and you have to demonstrate, or that's before solar, and then when solar's added, you have to demonstrate that you get an ERI score of 15, 1.5. So there we go. Now, here's where Carbondale made amendments to the section that talks about compliance paths and what's required.
Keep back up.
Yeah.
So for Pickens County, they just eliminate the other options and they just go with ERI.
That is basically what it says, because if you go into 401.2.4, it says that all new residential dwelling units have to comply with R407. So in reading their amendments, that would be how I interpret it by what the amendments are saying. That may not be the intent of what they were trying to do, but as I read the amendments, that's how I interpret it. Yeah. All right, so Carbondale. Carbondale says that they have amended, and they now have a table, which is their R401.2, which is their residential tier classification and minimum efficiency requirements. Now, the charging section basically says residential buildings, including single-family homes, duplex structures, and townhouses, and multifamily buildings, including residential portions of mixed-use projects, tier classification and mandatory requirements shall be determined in accordance with Table 401.2. Tier 1 classified single-family dwelling and individual dwelling units in multifamily and single-use buildings shall be allowed to comply with Section 401.2.5 and either Section 401.2.1, 401.2.2, and 401.2.3, which is basically you have the option of going prescriptive, total building performance, or ERI. That is if you fall under Tier 1. If you are a Tier 2, Tier 3, or Tier 4, it's going to be designed and constructed to comply with Section 401.2.4. All new residential construction shall also comply with the requirements of Appendix CB, Electric Ready and Solar Ready Code for residential buildings as adopted herein. So here is the table. Again, my apologies, I couldn't get the information to translate, and I'm always afraid to type it in that I'm going to inadvertently miss a letter, miss a number in there, and then cause a problem, so I just cut and paste. I'm happy to explain it. So house size or single unit in a multifamily, if you demonstrate that you're less than 1,750, then you are only required, if you choose this pathway, to get a HERS before renewable of a 60, and then your final HERS score with after renewables would be a 40. And it doesn't have anything listed in there if you are also utilizing gas. So it's just 60 and 40 in all of this. For Tier 2, and you are 1,750 to 3,999. Before renewable, you're going to have to get a HERS score of a 58, a final after renewables of 38 unless you have gas. Then your after renewable is required to demonstrate a score of 28. For Tier 3, 4,000 to 6,999. HERS before renewable, 54. Final with renewables, 34. And if you have renewables with gas, it's 24. Tier 4, if you are a building that is larger than that you're 7,000 square feet or larger, then it's 50 before renewables, Your final score with renewables is 30. Unless you have gas, then it's required to be 20. Now, there are some footnotes that apply to all of these. So if you are building in Carbondale, please be aware of this table because it's going to determine which compliance path you use and what you have to do for it. All right, so here are the values, and don't mind me as I struggle to get up. All right, here's the values that you would find as if you were looking at the 2021 code book. This is if you're in climate zones 5, 6, 7, and 8. Here are the amended requirements for Pitkin County and Aspen. So for Aspen, they have a row, which is the middle row there, that is for new construction and addition. These are the values that you're going to have to comply with. If you are Aspen and there are alterations, then you're going to have to comply with this row here. And I think that the wood framed walls might be incorrect in here. I might have put the wrong one in there because it should be R40. So my bad. That is a correction I'll have to make before I send it out to you or verify on that. All right, so if we look at these tables, we're going to walk through these tables and how they relate to the thermal envelope and the various components of that thermal envelope. The first ones that we're going to look at is our fenestration. So you can see on the screen here, here's 5, 6, 7, Pitkin County. Aspen is if it was new construction. Aspen if it's an alteration to the home or the residential structure. These are the specified requirements. Remember, these are the maximum it can be. You can do better and have lower numbers. Now, here's where it gets to be a little, I guess, built-in flexibility unless you are in Carbondale and what was, I forgot the other, Pitkin County, where they specifically said basically unless you fall under these very special criteria, you're just complying with 407. If you are going with the true R value of that table and just going with the R value of the prescriptive option, then there are some sections in here that apply to the fenestration. One is you can do an area weighted average of your U factor. You can also do an area weighted average of your solar heat gain coefficient. There's also this nice little flexibility built in where you get an exemption from that U factor and solar heat gain coefficient requirement that we have in the table for up to 15 square feet of that fenestration. It's only allowed if you're going with the R value table. If you're going U factor or total UA, it's already built in, you don't get to do it. You also have an exemption for opaque doors of 24 square feet from the requirement out of the R value table, and you say, where is that listed that there's an R value for it? There used to be. This was in there way back when, and it's never really been moved. But you still have to maintain that you have continuity with that thermal envelope and the R value with it. So now let's talk about our ceilings. If you notice here in the 21, there is a move from the R49 to the R60. And the other thing that was really nice is Pitkin County threw in here if you're going to use insulation entirely above roof deck, you now have to have an R35 continuous insulation. It's a component that comes in as an option in the 24, so they kind of brought that in. And you say, why would you do that? Because when you have multifamily, they're typically building out of the IECC, and a lot of time, the multifamily places their insulation entirely above roof deck. And so until that's in there, technically, if they're building above roof deck, they have to follow the requirements out of the energy code. The energy code in the 21 doesn't have any distinction between an if it's in the attic or if it's above roof deck. So the above roof deck insulation would be that R60 requirement, unless you're in the community that amended it to have an R value for insulation entirely above roof deck.
And Hope, aren't we coming back down?
In the 24, yes, it does go from 60 to back down to 49. Yes. What was that?
Why?
Well, that's kind of a loaded question, but what I will tell you is it was a heavily contested concept in the 21 to have it moved to 60. And in fact, the amount of manufacturers that were actually against it was crazy, and how it got in was crazy. But ultimately, the reality is they took a look at it. It was highly contested as far as one of the reasons why the code wasn't necessarily getting adopted unless they were forced to adopt it. And so one of the concessions that happened in the 2024 is that they reduce the R value for the ceiling, but they also made up for it in other areas of the code. But that was a concession kind of had happened in the whole process to let's kind of be a little bit more reasonable here. And they said, that's fine, we'll be reasonable here, but we're going to make it up in other locations of the code, basically. It was called the big omnibus give and take or something like that.
Yeah, we're trying to shut it in, Franny, because we're referring down to shut it in.
Yeah, well, that's in locations outside of Colorado. When they were adopting the 21, that was what a lot of people cited as to why they would make one amendment. It was that the ceiling would still stay at the 49, because they're like, why am I going to do it, change it for a 3-year period with my contractors, and then tell them, 3 years later they can go back to what it was. They're like, why are we going to do that to our building community? We want to ensure that we're getting really good installs, and this back and forth thing is often difficult. Here in Colorado, we didn't have that option, and so the good news is when the 24 is adopted, you can go back to the 49 design that you probably have been doing for the last 2 decades. So,
So does that mean if you're submitting to keep the county rate, which is still 21, you can say, hey, 24, you're going back to 49?
nope, because by state law, they can't allow the reduction unless you are utilizing a different compliance path, such as res check, would allow for the trading of it, but still, it starts off at that R60 level and not the R49 level. Great questions, though. All right, so if you are able to go with the R value option, there's a little bit of flexibility for you. So this is where the flexibility could fit for you, is the fact that the code allows, if you're going with the R value option of the prescriptive path, instead of doing that R60, it will allow you to reduce it down to an R49 as long as you get an R49 up and over that top plate without compressing it. And the idea of that is, obviously you're going to have a raised heel truss or an energy truss for that. But the idea is, typically in the past, you might have had an R60, 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 and then we got compression going on here, so it dwindles down, and maybe it goes down to an R25 at that top plate area. And then if you did the area weighted average, the theory is you would still be at about an R49. So they're saying, why do we need to worry about the math? If they can get an R49 everywhere, including up and over that top plate, and not have it compressed, then what's the difference between that and the 60 compressed down and doing the area weighted average? So that's kind of the concept for that. But it is only available for that R value option, and you have to demonstrate that you can meet that, which is basically, if you're using batt insulation, you're going to need, I think it is 14 inches at that top plate to be able to accommodate for the bat insulation. That's how much space it needs to have that uncompressed R49. Another option of flexibility for the R value option of the prescriptive path is for up to 500 square feet or 20%, whichever ends up being the smaller amount, you are permitted, when you have ceilings without attics, to install an R30 in that area. Now the idea is, right, you have that bump out. That bump out typically doesn't have that full depth of attic space. You just have a little bit of space. So the idea is you could get an R30 in that little bump out area, and it works because it's not a huge amount, right? You're just doing this nice little seating window area that's 200 square feet. So you just have a 200 square foot that only is an R30. The other thing is eave baffles. So if you have a vented attic and your insulation is resting at the ceiling level, then we have to have those eave baffles. This is not only a requirement out of the energy code, it's also a requirement out of the residential code. If you go into 806, it talks about you have to maintain a 1-inch air gap at all of the vented area. Now, the idea is the understanding that air doesn't just stop right here because you say, here's my baffle. It goes to the path of least resistance. So if there's not a baffle in each bay, it's just going to cause havoc in the bays that don't have baffles. So the energy code says, hey, by the way, don't forget, you're going to put it in every bay. All right, wood-framed walls. So our wood-framed walls, we have some pretty significant differences, but the really nice thing is, in all that is said and done, is the fact that you have options in how you're going to meet that. You can do the cavity-only option, which could be an R30, R40, right? It could be a cavity plus continuous option, and then there's this new one of continuous only. And I know a lot of people are kind of concerned about that. They're kind of like, well, that's an awful lot of insulation that's required to be placed on the exterior. Can you handle that? I have projects before this was ever permitted by code. They did an alternative method, means, and material, and all they did was put continuous insulation on the exterior. And it worked out great. They were in climate zone 7 too, so it wasn't as if. And they used heat pumps. They had backup heat, but they also had heat pumps. And from the residents that we spoke to, they're like, we've never had the backup heat kick on. Our heat pump's been able to handle it. So that design is possible. Obviously, there are some concerns. Again, not condoning one option over the other, just bringing to light it is possible. All right, so here's an example on the screen that probably not very many people can read. You'll notice that it says here an R20 insulation, and then it's also showing here that we have 1 inch of rigid insulation. Does this work? What's the R value of that rigid insulation? Could be. Remember I said that mineral wool has rigid insulation products and they go from a 3.8 to a 4.3? That's not quite an R5. And if we take a look at the styrofoam ball rigid insulation, it does not get an R5. So here's once again in 103.2, and it states you have to provide the R value and the material that's getting utilized. Plus, there are some issues because it has to also work with what the vapor retarder strategy is too. Now here's another one here. It talks about what the design is for that rim joist, but we'll get to that later. I just realized we'll get to that later. So let's talk about our mass walls. So our mass walls, and again, they have to follow the requirements of 402.2.5. There's two numbers listed there. The first number is if it's being placed on the exterior side of the wall. If it's being placed on the interior side of the wall, you're going to utilize the second number. Now, what if it's placed in the middle? Which number are you going to pay attention to? How many of you say the first number? How many of you say the second number? Okay. So if we come back to the footnote, because remember, footnotes are your friend or your foe. It states if the insulation is more than halfway on the interior side. So if it's in the middle, it technically has not met that more than 50%. So I would look at it as the first number. Now, if it's located more towards this side of things, and that's the design, right? Obviously, when you go out into the field, no matter how well you plan for it, there may be a little wonkiness. Maybe it's 51 by the time you pour and everything else. Am I going to get really bent out of shape about that? No, because the design showed it was going to be in the middle. The intent was I was using that first number, and that's the reality of it. Now, if things happened and that middle one all of a sudden was pressed all the way against the interior side, that's when I'm going to have an issue with it. But 402.2.5 for our mass walls, the really great thing about this one, where the commercial side doesn't really take that into account, is we have all of, when the highlighter works, we have all of these materials that are already deemed to comply as a mass wall. So we know if you're one of these, you're going to follow that part of the table. Or it also gives you an option that if by chance you have a heat capacity that's equal to or greater than 6 BTUs, then you're also considered to be a mass wall, just in case it's a new material that falls outside of these parameters. If they meet number 2, mass wall. All right, let's talk about our floors. As you can see here, floors have some fun items to it. And did I lose my screen? All right, well, okay. So 402.2.7 is the section that deals with floors. And I probably should have mentioned this at the beginning, but most people look at 402.1, they figure out, okay, what's in the table, what do I need to do? The part that gets skipped is 402.2. 402.2 is our insulation installation section. And in that section, it provides a heck of a lot of flexibility on how you're going to design your building. So I'm hoping more and more people take a look at 402.2 because it is a great resource in trying to figure out how am I going to design this. I have this really funky thing. Maybe there's something in there that gives you a hint like, hey, here's an exception. Use it. It's there for a reason. All right, so floors. It says, number 1 says it has to be in constant contact with the underside of the subfloor. We've known that forever and a day. That's been in there forever and a day, and it says that on the commercial side. But there's also a second option. The second option says, well, you don't necessarily have to have it in constant contact with the underside of the floor. We're going to allow you to rest it on top of chipboard, as long as you take those above grade wall insulation values and extend it down into that floor cavity. Great possibilities, right? Gives you some good options out there. Now, the third option is dealing with basically this similar item that number 2 gave us, except for instead of resting on that chipboard, you get to rest it on top of continuous insulation, as long as you extend that wall cavity insulation or that wall insulation into the floor cavity, so that we are ensuring that we're maintaining the continuity of that thermal envelope, of that insulation, right? So here's a great example of they were using continuous insulation. They blew the floor cavity or the floor insulation that was going to rest on top of the continuous insulation. And I know it doesn't show it here, but the wall cavity went down into the floor cavity itself. So it was continuous. All right. Now here is a really fun one. This is really dealing with those basements. So basements have a little bit of funness to it. So basements, as per what is listed in the definition of a below grade or basement wall for residential, is it has to be 50% or more below grade. So there are possibilities, and I see it a lot, especially when you have those walkout basements, that you might have a section of the wall that's going to be a below grade wall, and sections of the wall in that basement that's going to be considered above grade. And so typically how I see that designated on plans is there'll be maybe a dotted line or a hashed line, a hashed area that'll go right in front of, you know, this is my wall. This is the wall that is going to be considered above grade, and so it will utilize the above grade walls assemblies. It'll have something of that nature, and the remainder of the areas to be below grade. And that's typically something similar to that I'll see as far as a notation for it. All right, slab on grade. So slab on grade, here's our R values. I was pointing it to my screen to show you all where I was. You'll notice that there's footnote D. Footnote D tells us, hey, if it's a heated slab, guess what? Insulate it to an R5 in the entirety underneath that slab. Now, R402.2.9 tells us the slab edge insulation is only required when you have a slab that's 12 inches or less below grade. It must extend for the distance that is shown in the table. What do you see as far as the distance? 4 feet. What's your frost depth in an area that you typically design to or inspect to? 4 feet? All right, so then you're probably looking okay on this.
I like it.
You like it?
I like it.
All right, Derek likes it. So one of the things that you have to keep in mind is you do have a little bit more flexibility out of 402.2.9. One is one of the options of how it can be installed where you have that 45-degree interior angle. We'll talk about that in a minute. But the one thing you do have to be aware of is in the 21 for the residential provisions, slab edge insulation is not permitted to be traded. In fact, it's never been permitted to be traded. That was never the intent with it. ResCheck had a glitch. It wasn't caught until recently. So now we are really trying to illustrate if you're on the 21 or later codes, slab edge insulation is not allowed to be traded, and you won't have that ability in ResCheck. 24, that's a new story, but 21, no. So here are all the options that you have for configuration. We talked about all of them on the commercial side except for this one. This one allows for a 45-degree angle to happen on that insulation because, you know, people like to have, what I always hear is the carpet tax. They aren't going to have anything to, you know, nail down to or have the fun with, but there is a trade-off for that. What do you notice there? Anything? How about where the points meet? Right? You got it. you don't have the depth going on. So what are we going to have at this spot right here? Yep, crumbling. So you do have that flexibility, just realize there is kind of a trade-off for it. All right, so if we looked at this plan, would you say that we're good? No, yeah, you're right. We got slab that's less than 12 inches, and we have no slab edge insulation provided on these plans. I'm so glad I have these plans because I use these plans like you wouldn't believe. All right, another thing to keep in mind with that I see missing often is the idea that when you have exterior or you have exposed foundation insulation, you have to protect it. And whatever you use, that covering has to extend down 6 inches below grade. Because guess what this is? This is not 2 years down the road that I'm like, huh, that's really interesting, all those pop marks that have appeared. This was at final inspection. What do you think's going to happen? I don't know if you know this, but sometimes it snows. And sometimes people have to shovel the snow. And what do you think's going to happen when that shovel hits that exposed insulation? That area is not going to last a single winter season. And if it did, what do you think kids are going to do? Have you ever seen kids not pick at a scab? After you tell them don't pick at it, what do? Right in front of you. Did you say not pick at it or pick at it, right? I know my kids when they were little, if they saw that, especially my daughter, she would be picking at that all the time. No, they're going to pick, well, probably both. They'll kick it and pick it because they're going to try to figure out what they can do with it. All right, let's talk about crawl spaces. One of the things we have to be aware of when it's a crawl space, and even for attics for that matter, is it a vented crawl space or an unvented crawl space? Because if it's a vented crawl space, this isn't a section of the code that we're going to worry about because we're going to look at that insulation at the floor level. If it's an unvented crawl space, now I'm going to pay attention to what this table says and what the requirement is because our thermal envelope needs to extend down on the walls of that crawl space. So if you look at the image on the left-hand side, is that a vented crawl space or an unvented crawl space? Vented. Why would you say vented? There's no, yeah, exactly. There's no insulation at the wall. Where it does show the insulation is in that floor cavity, which means that they did the correct thing, that this vented crawl space has their insulation in the thermal envelope located at that floor level. They get a kudos from me on that. Now, the right-hand side, the right-hand side, vented or unvented? Yes, because we got vapor retarder covering the soil there, the dirt, whatever you want to call it, and it extends up the wall like it's required, and we have insulation on the wall. So that takes us to the end of our insulation section. Now we're going to have the fun part of talking about air barriers. So I always like to talk about the fact that you should never have insulation without an air barrier because insulation gets its R value by stagnant pockets of air. So if you don't have an air barrier, what happens when the wind blows? Yeah, you got air exchanges and it strips those stagnant pockets of air. So you have a material no longer performing the way that it should be performing. And so you really do need that air barrier, and you should always have that Siamese twin concept going on where you have an air barrier wherever you have insulation. Now, I like to equate that to, think about it when you're out in the fall, you wear a fleece jacket. I wore a fleece jacket today in the fall because you just kind of, there's a little bit of a nip in the air. And you're very warm until you have that breeze that comes through, right? Exactly. That breeze comes through, and what does it happen? You go, whoo, oh, that was cold, because you felt it, because the air moved onto your skin that you could do it. But if you wore a windbreaker with that, appropriately named, right, windbreaker, that all of a sudden, all that heat that you've generated isn't getting stripped out by that wind going through it. Now, I always have to look in the room, because I told this to, I said windbreaker to college students, because I have a architect program that I do their energy code training at. And I said windbreaker, and they're just like this to me, and I'm like, okay. And I was trying to figure out what was going on, and then finally this one kid, he goes like this, ever so slowly. And I'm like, yeah, what's up? And he goes, did you mean a shell? And I'm like, oh my gosh. So now I look in the room. Who am I talking to? I'm talking to my peeps that are like, yeah, you all know what a windbreaker is. Otherwise, sometimes I have to say a shell so that I hit my, I guess, demographic of the audience. So anyway, the idea is we want to kind of protect and ensure that our insulation is performing the way that it should. We don't want lazy insulation. So if we look at the image on the screen, what's that discolorization on that insulation?
Well, that's a filter.
Exactly. It just became a giant filter for this building. So I was in this building. I saw this exposed. I should have taken a picture of it because we were running an event or whatever. And I'm like, oh, they really need to cover that up. It was just one little section. And I thought, not a big deal. I thought that when I came back that next year, it would be addressed. It was not addressed. They still had it exposed, and I took a picture, and I'm like, I'm so mad at myself that I didn't take a picture of it the first year so you could see the drastic difference between the two time frames of the same insulation, because it was, I'll say this was definitely significantly worse. And it's all dirt. So what happens when that dirt takes up the space of where the stagnant air pockets would be? Do you still have the same R value going on? Nope. You reduce the R value for it. The other thing is 103.2 also says that you have to provide a detail. A picture is worth 1,000 words, because if I show a picture of something, I am more likely going to get that out in the field as opposed to writing all of that. And here's a great example. How many of you have ever had a conversation with another person in the code world and said, hey, doesn't 103.2 say XYZ? And they say, that's not how I read it. I read it as it's STU. And you have the discussion. Those words haven't changed. They're the same words that this person's reading and this person's reading, but due to each of their own life experiences that play into how it's interpreted, you have often different interpretations. So if you have a picture, which is why it's required to have a detail, it kind of eliminates a little bit of the concern of, am I interpreting this correctly? All right. So we do have testing requirements, right? We have to test our building. We have to demonstrate that we don't exceed 3 air changes per hour for our climate zones. But there's a new option in there. The new option is that CFM per square foot, that true testing metric that comes into it. It's allowed for if you have multifamily or you have a single family home that's 1,500 square feet or less. So it really is addressing those smaller dwelling units that really did have a difficulty because they didn't have the volume for the air changes per hour. So it's a really good addition to the code. All right, Let's go through our lovely table 402.4.1.1 and talk about some of the things. So the first one is, hey, you better make sure you got a continuous air barrier all throughout your building. Has to, you might have to change locations and so forth. That means thinking about your ceiling level, if your insulation is in the attic, or if your insulation is entirely above roof deck, then that's the area that you need to pay attention to for air barriers. The other thing to keep in mind is you cannot use air permeable insulation as an air barrier. So here's an example of where they place notes. One says, our continuous air barrier is going to be the airtight drywall approach. That's what they're utilizing. That's a difficult one to really ensure that you're going to be able to make it, but there's nothing saying you can't use it. The other one says just durably seal everything to ensure that we have that, and not necessarily specifying exactly what that material is going to be. Now, I remember when zip panels came into the scene and they were calling out, oh, well, we can be an air barrier system. They can, absolutely. And they demonstrated that they can do it because they just can't exceed that 0.004 CFM per square foot of air leakage. And they do that. So there's a lot of different materials out there. It could be house wrap. Again, it's got to be installed the way that it needs to be to meet that criteria. Now, as far as zip panels goes, remember that you can't use your hand to flatten the tape. It has to be the specialized roller. And guess what? That specialized roller says zip on it, so it puts a little indent in the tape to let us know that it is the correct roller being utilized. All right, ceilings and attics. All right, we got to ensure that we have an air barrier in alignment with whatever our insulation is. So that's taking into account things like maybe when you are utilizing part of the roof trusses as it, you need to make sure that you include that. Also, attic access openings. I think this has been, it's been in the code for a while, and I think we're probably fairly good at ensuring that. Just make sure that you have that weather stripping or sealing of some sort, because often when testing, if it is leaking, that's an area that can have it come leaking in, and it's a simple area to ensure that we just meet that. Now, here's an example of it out in the field. The little latches are not required by code. I'm seeing them a lot more out there just because it does help, keep it a little bit tighter so there isn't that air movement going on. It's not required by code, but I'm just seeing it more and more now. The other thing is, keep in mind when you have a change in ceiling design like this, you have to ensure that you maintain where that air barrier is going to be and that is sealed up too. So like here we have some lovely architectural features. These are things that we would have to pay attention to ensure that we are keeping that air barrier in alignment with the design of the ceiling and where the insulation is going. Walls. Walls, we have to ensure several things. One, let's talk about the bottom plate. That bottom plate has to be sealed. So we should be seeing notes listed on here. And as you can see here, it's calling it out, continuous beads of sealant. We also have to do it at the junction of the top plate. And as you can see here, it also demonstrates that they are sealing it. Here's an example of it out in the field that they actually did a really good job with it. What about this one? What do you guys think? Good, bad, ugly?
Came up a little short.
So I'm assuming you guys are referring to the seal here and the, I guess, gap there. What's seal for? Yep. We have to have that capillary break because that foundation wall is going to draw moisture in and bring it up, and water and wood don't always get along. And we kind of like the idea of, I don't know, not having our buildings fall down for wood rot. I don't know, it's kind of a crazy concept that we don't like being on the news for, right? So seal is a capillary break. It's actually is not to be used as a sealant. It could potentially maybe be considered as a seal if everything was snug and there was no way for air movement to come through there. But unfortunately, construction is not perfect. I don't know if you guys knew that or not, but there are things that happen. There are maybe minor defects in the wood, right? The grain of the wood. It's not going to quite work. So setting a project up to succeed is not necessarily utilizing that seal. What do you guys think about this one? I gave you a hint. The arrows came up. I forgot to put animation on it. So they sealed here. Now that might have been part, because this was multifamily, right? So it might have been part of the requirement for their rated assembly, but for me, as far as air barriers and air movement, that sealant should have also been, or it should have been located here. So here's a great example of where they sealed it. Now, when we start talking about multifamily, a lot of people are concerned about those common walls, the party walls. And most fire-rated assemblies now already include the requirement for air sealing of them. It was never a condition of voiding the quote-unquote rated assembly. And like UL and some of the other entities out there got tired of writing letters saying, no, it's included in the design of these particular assemblies. They just started putting it on their assembly, so they didn't have to keep writing the letters for it. So they're sealing it up in the locations that it should be. Now the other thing is talking about knee walls. Typically you see them in attics, but I've had knee walls in a different part of the country. They're all over the place in crawl spaces, and it's part of their thermal envelope. So if it's part of your thermal envelope and you have that knee wall, not only do you have to insulate it, you also have to have an air barrier on it. And I have lots of people who say, well, they didn't seal that air barrier up. And I'm like, you are absolutely right. They got out of the way so I could take a picture of it. So they weren't at the completed process of it. Now let's talk about windows and doors. You have to air seal those windows and doors. Now, you also have to install it per the manufacturer's installation instructions. Many of the window installation instructions do call out that they want you, after you put everything in, you have your fins in, it's sealed up, you got your shims in place. It does talk about stuffing bat insulation in all of those crevices. The shoving of the insulation in those crevices is not for the air sealing component. It's to basically kind of put something there as a little bit of a blocker. It also talks about then you're going to seal around those windows. So just be aware, while it does talk about putting that bat insulation in there, that's not what they're calling out as their air sealing of a window. But window manufacturers, one thing that they have really wanted me to stress to everyone is there's a lot of sealant getting utilized. Unfortunately, people are also utilizing that fast expanding foam. You should not be using that fast expanding foam because it pops the seal of the window. The windows obviously don't perform, and it causes all these issues. So make sure that you are using that. Now this one was missing a lot of sealant, whereas this one did a good job of sealing. This one also did a good job. It's really hard to see. I was really excited because this was at a location that they were just starting the energy code. They've probably been doing it for about a year, and they were trying to get everybody trained. And so I went out there to walk this project with them. And it was really exciting because they're like, see, look, they use the right stuff on these windows. Because in the past, apparently, that was an issue. All right, let's talk about rim joists. So rim joists. Rim joists have to have an air barrier. You also have to seal them up. There's a lot of blue there. This table doesn't necessarily have a lot of new requirements in it. What they do have is a lot of rewording, because what they're finding is that it's not getting put on the plans correctly, and it's not happening out in the field, so they keep trying to change the wording around to really convey what they're asking for. But basically what they want in that rim joist area, they want it sealed up so that we don't have that air movement going on, and they want to ensure that you also are putting an air barrier there. Now, in this particular design here, how many of you say that it's a good design and you're okay with it? Everybody's hand should go up, because we have, yep, exactly. We got spray foam behind it. And because there's spray foam, it has to have that ignition or thermal barrier protecting it from the interior side of the structure. So that's what the batt insulation is for. The install of that batt insulation is atrocious, and if it was there for the thermal envelope, they would fail all day long, but it's just there as the ignition and thermal barrier. Floors, you have to have an air barrier involved with it, and you also have to like seal up those junctions that are going on there. So in this instance, this area here would have to have an air barrier. So would this area here. Basement walls and slab and foundations, we got to ensure that we have the typical design that's required out of 408 of the IRC, right, our vapor retarder. We also have to ensure that we have insulation in there. And the big thing is if we have any penetrations through that foundation or through that slab, that they're sealed up, which makes sense, right? Shafts and penetrations, we want to seal up where those shafts are, right? Ensuring that as they're entering and going through that thermal envelope component, that they're air sealed and that the shafts themselves also contain an air barrier. Penetrations, we want to seal up all those penetrations. Here's an example. They're sealing here. They are using OSB as their air barrier for all of that. So these areas would be sealed if we were there at a later date. Here's a great example. I have a builder friend that I go out and take pictures and visit all the time. He's really energy focused. And his policy is if you're going to put in a 2-inch pipe, you are permitted to bore a 2.5-inch hole. The idea is that if it's not a 6-inch hole that's going in there, there's not a whole lot of sealing that has to happen from that. But it also takes into account some of the expansion and contraction that's obviously going to happen with our environment and with our climate. Wow, I think I would learn how to speak, but. So that's his philosophy, because otherwise you're looking at something like this and figuring out how are you going to address that. If you look right here, you could actually look through the wall. So that usually indicates their question was, I failed my blower door test. Why do you think I failed my blower door test? First thing I'll do is walk around the exterior of the building, because a lot of times it's something as simple as this. Now, chances are they said, hey, go seal up that penetration. They took the caulk that they were, putting on the bathtub and thought, well, it's sealing up the bathtub. Why can't it seal up right here? Well, that's outside. You got to have something, remember it says it's got to be, you know, appropriate and compatible. And is that something that can be used on the exterior? Can it be exposed to UV? Can it be exposed to weather? Those are all things that have to be taken into account for that. What do you guys think about this one? Good? Bad?
Kind of open.
All right. I will tell you, I'll be honest with you. This is, again, hope jumping out of a car, because I saw this, and I'm like, ooh, I got to get a picture of that. Ah, you got it. I saw this at first. This is an issue, right? But they utilized a flashing system designed for line sets. And so that design of that flashing system takes care of the odd configuration that we know those line sets are going to have. And so at first, like I said, I jumped out because I thought, oh, that's a bad one. And then I got closer and I'm like, oh, they got the flashing system. So this does not always mean it's a bad thing. Are they going to have to seal it up for water? Absolutely. But as far as the energy code goes, it's this that I care about. Narrow cavities. This is new in the 21. And basically, if you have a narrow cavity that's an inch or less, you have to air seal it. So a lot of times what I see is they are just putting in, you know, grabbing a can of you know, fast expanding spray foam and just bloop, there we go. And typically I just see it as a note on the plans. Garage separation, you have to have an air barrier to separate your garage from the rest of the dwelling unit. Is this something we need to be concerned with? How many of you say yes? How many of you say no? I say no. And you say, Hope, you're just telling me I have to do this. Let me explain why. What if we go into 302.7 of the IRC? What does it tell us? We have to separate our garage from the dwelling unit wall with a 1/2 inch or 5/8, right? Depending on where we're at. What do we have to do if we have living space above? Separate our ceiling floor level with 5/8 type X. The IRC takes care of that. But am I going to ensure that it's shown on there? Absolutely. But if I have to take my time between this and something else, this I know is getting addressed on a consistent basis. I'll maybe focus on something else. I still worry about it. I still ensure that it's there, but I may not worry about it as much as some of the other things. Recessed lighting, just like on the commercial side, IC rated. Air leakage, it's got to be sealed up from the housing and the wall or wherever it's being, or ceiling, wherever it's being done. We have to seal up holes that are being created by wiring, plumbing, or other obstructions in the air barrier assembly. So on this one, you'll notice that we've got jacks up here. We're also showing down here some sealant. Where am I paying attention to the air barrier? What assembly? Where's the insulation at? It's resting on that ceiling level. So this is what I'm paying attention to. That gypboard is being my air barrier. So the penetration is going through the gypboard. So this is the ceiling, the S ceiling at the C ceiling that I'm paying attention to as far as air barriers and the energy code. All right, tubs and showers, when they're located on the exterior wall, we have to have an air barrier. This is the assembly order that it needs to happen. Sheathing, insulation stud, air barrier, then tub shower. So that's the order that we're looking at. Now, here's one that I was actually walking by, going into a different room, wasn't even looking at this, but I got into the other room and apparently I had saw enough of this that in my brain I'm like, there's something wrong. So I went into the room, I'm looking at it, there's some insulation thrown on there and I'm like, oh, we got insulation. We got insulation here, we got insulation here because these are where our exterior walls are. And I'm like, oh, That's why this is all pulled out, because there's no air barrier. And so they pulled all that out because they now have to put an air barrier separating that tub from that insulation and then re-insulate it. Here's another example of they've used OSB. You can use OSB. You got to seal it all up. But here they had a 2x4. Are you going to get that same R value in a 2x6 wall with a 2x4 stud? Last time I checked, you aren't going to get that R30 or R40 in 2 inches. If there is a material out there, please let me know. I think that's huge. That would be a good thing to know. And then here's an example with the shower. Now, this is where we're going to want an air barrier. Now, remember right here, even though we have blocking installed there for our grab bars, it doesn't state that grab bars are exempt. That area is exempt from having to have that insulation there, so you still should have insulation back behind there. Here's one that I love. I know I dwell on this. I can't tell you how many times showers and tubs, if you look at this, you think, oh, that's not bad. And you look there, and it's like, ooh, we need to have an air barrier here because they cut all around here. Not only that, when you looked in there, that wall didn't have any insulation in that wall either. So that was could be a little bit of a problem. All right, electrical or communication boxes, you have to seal them, air seal them when they're penetrating through the air barrier. One of the other opportunities is you can comply. What it does say is not that you have to have a self-sealing box, but if you do install an airtight self-sealing electrical box or communication box, it does have to demonstrate that it meets NEMA OS4. So it'll have to have that shown on there. But we just want to make sure we're sealing things up. And speaking of sealing, let's talk about our ductwork. Our registers, as they penetrate wherever the thermal envelope is, walls, floors, ceiling, whatever, we want to seal up and seal up where it is in communication with whatever the subflooring is. And I know I didn't express that very correctly, but. So here's some examples of it being sealed up where we want it to be sealed. Just like on the commercial side, if you have concealed sprinklers that are located within the thermal envelope, only if they're located where the thermal envelope actually resides, you do have to seal them up in the fashion that is specified by the manufacturer. And as we discussed earlier, we don't have those yet, so start asking for them. Because here's an example of one that I went out with the National Fire Sprinkler Association, because they're the ones who put that in. They come out periodically and we walk around things, and this community always says, come out, see what we're doing so we know what we're doing right and what we're doing wrong so we can make sure that we're doing things. And so we had this. They were horrified with what they saw in that project. But here's an example of why would we care? Because I will tell you, if you see how much gap is there, that's really going to have an impact on your blower door testing and your results. And just be aware that in the 24, your blower door test results are reduced. So these are the types of things we want to ensure that the little things are going to make a huge difference in the future. So let's get them done now so it'll make it easier for us in the future. And that's it, guys. Thank you very much for listening to me blabber all morning long with you. And here's my contact information if you have any questions. And as Gina mentioned, this is a series. We looked at the thermal envelope. I think next one is what? Commercial mechanical?